Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into one of Earth's most haunting questions. What if we're not the first civilization to call this planet home? If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The question settles into the mind like sediment in still water. 4.5 billion years stretch behind us, layer upon layer of stone and time, holding secrets we may never uncover. The Earth spins through space, carrying its cargo of mountains and oceans, forests and cities, and somewhere in the deep strata lies the possibility that others have walked this path before. Each rock tells a story. But rocks are imperfect narrators. They speak in chemical whispers and crystalline fragments, in the arrangement of minerals and the absence of what should be there. The limestone remembers ancient seas where trilobites scuttled across silted floors. The sandstone recalls desert winds that blew when the continents wore different shapes, when the Sahara lay submerged beneath tropical waters. But between these testimonies lie gaps vast, yawning spaces in the record where entire epochs simply aren't. Scientists call it the principle of uniformitarianism. The present is the key to the past. The forces shaping Earth today, erosion, volcanism, plate tectonics, the patient work of water and wind, these same forces have been sculpting the planet for billions of years. It's a reassuring thought, this consistency of natural law. Rivers carve canyons with the same persistence now as they did when the first oxygen bubbled into ancient skies. Volcanoes build and destroy with the same elemental fury that marked Earth's earlier centuries. But uniformitarianism also means that evidence disappears with the same reliability that it forms. Consider the most basic question: if a technological civilization existed on Earth 1 billion years ago, what would remain? The pyramids, those monuments to human ambition carved from Cretaceous limestone, will be dust in 50 million years. Mount Rushmore will weather into unrecognizable rubble. Our cities, compressed into thin layers of unusual metals and plastics, will leave only the faintest chemical signature in the geological record, a momentary spike in aluminum and rare earth elements, perhaps a brief abundance of isotopes that tell of nuclear energy. Only took 4.5 billion years for us to ask this question at all. The fossil record preserves perhaps 1% of all species that ever lived. The rest vanished without a trace, their stories dissolved by the patient chemistry of time. Soft tissues decay within years. Bones dissolve in acidic soils. Even shells and teeth, the hardest remnants of living things, crumble under the pressure of deep burial and groundwater flow. If complex life organized, perhaps even intelligent, arose before us, the odds of finding direct evidence approach the infinitesimal. Yet, here we sit, proof that complexity emerges from this planet's particular alchemy of elements and energy. The Drake equation, formulated to estimate the number of communicating civilizations in our galaxy, contains variables we can barely guess at. But perhaps we've been looking in the wrong direction. Perhaps the most relevant application isn't to distant stars, but to deep time on our own world. How many variables favor the emergence of complexity? How many times might those conditions have aligned during Earth's long history? Deep time has a way of making the impossible seem merely improbable. 1 billion years is enough time for continents to drift across the globe, for the Atlantic Ocean to open from a narrow rift to a vast expanse that separates worlds. Mountain ranges rise and erode completely away, their granite hearts worn down to sand and carried to distant seas. Entire oceans open and close like slow, planetary heartbeats, leaving only suture lines in the rock where ancient seafloors collided with continental margins. In such vastness, the emergence of organized complexity seems not miraculous, but inevitable. How many times inevitable? The question carries its own peculiar weight. We know that Earth underwent at least 5 major mass extinctions, events so catastrophic they reset life's trajectory entirely. The Permian extinction eliminated 96% of marine species, leaving behind a world so emptied that geologists call the following period simply the Age of Recovery. But recovery from what, exactly? What forms of organization might have vanished so completely that their absence shapes the patterns of what came after? Consider the chemistry of our atmosphere. 21% oxygen seems natural to us, but it represents a careful balance maintained by living processes. Too little, and complex life suffocates. Too much, and the world burns in spontaneous fires. For billions of years, this balance has held steady, regulated by feedback loops between plants and animals, ocean and atmosphere. But what if this stability itself suggests not emergence, but maintenance, the continuation of patterns established long before our own species began its brief experiment with consciousness? The minerals in Earth's crust tell their own quiet stories. Some rare elements appear in concentrations that seem to require biological processes to explain. Others show isotopic ratios that hint at industrial-scale refinement. Most scientists interpret these signatures as the products of geological processes we don't yet fully understand, but the uncertainty remains, like a whisper just below the threshold of hearing. Plate tectonics, that vast recycling system that drives continents across the globe, operates on timescales that dwarf human imagination. The ocean floors, Earth's newest surfaces, are never more than 200 million years old. Everything older has been dragged down into the mantle, melted and reformed, its secrets dissolved in liquid rock. The continents themselves preserve only fragments, scattered pieces of a puzzle whose edges have been worn smooth by time. Only took us a few thousand years to transform the entire planet's chemistry. Our industrial civilization pumps carbon dioxide into the atmosphere faster than volcanoes, creates synthetic compounds that never existed in nature, moves more sediment than all the world's rivers combined. In geological terms, we are a sudden spike, a brief anomaly in the planet's otherwise steady rhythms. But even our most dramatic alterations will fade. The carbon will be absorbed by weathering rocks. The plastics will decompose. The radioactive isotopes will decay into stable forms. Within 10 million years, perhaps 20, the evidence of our passage will be barely detectable. This is the haunting paradox of deep time. Complex systems can emerge, flourish, transform entire worlds, and then vanish so completely that their existence becomes only a theoretical possibility. The absence of evidence is not evidence of absence, but it is profoundly unsettling. We stand on a planet that has been experimenting with complexity for 4 billion years, and we see only the most recent results. The question drifts through the mind like starlight through space, patient, persistent, impossible to grasp directly. Earth keeps its secrets well, buried in stone and silence, in the spaces between what we know and what we can never know. The rocks continue their slow testimony, recording the present moment that will someday be someone else's distant past, holding mysteries for listeners yet to come. The Hadean Eon stretches across Earth's first 500 million years like a fever dream written in molten rock. This is the age of amnesia, when the planet burns away its own memory with each passing millennium. The name itself whispers of underworld Hades, realm of the dead, where nothing survives unchanged. Here, in the earliest chapter of Earth's story, any evidence of complex organization faces forces so violent they reshape the very atoms of stone, zircon crystals. Tiny grains no larger than salt represent almost everything we know about this primordial time. These mineral survivors form in cooling magma and resist the planet's attempts to erase them. Some carry chemical signatures suggesting liquid water existed even then, pooling in brief respites between impacts. Others contain traces of carbon arranged in patterns that hint at early life, or at least at the organic chemistry that makes life possible. But for every zircon that survives, millions perish in the recycling furnace of planetary formation. The late heavy bombardment peaks around 4 billion years ago, a cosmic storm of asteroids and comets that turns Earth's surface into a constantly renewed wasteland. Each impact releases energy equivalent to millions of nuclear weapons, vaporizing rock and sending shockwaves through the planet's thin crust. The largest collisions create magma oceans that remain liquid for millions of years, slowly cooling under skies thick with vaporized stone. Any organized structures that might emerge between these catastrophes face inevitable erasure when the next projectile arrives from the asteroid belt's chaotic dance. Yet even in this chaos, patterns emerge. The impacts follow rhythms driven by orbital mechanics and gravitational resonances. Periods of intense bombardment alternate with relative calm, creating windows of stability that last for millions of years at a time. During these quiet intervals, the planet's surface cools enough for water to condense, for chemistry to proceed along more predictable pathways. The first atmosphere thickens with volcanic gases. Primitive continents begin their slow emergence from the global magma sea. Scientists estimate that the Hadean bombardment delivered more water to Earth than currently fills all the oceans. Most arrived frozen in cometary ice, sublime instantly upon impact, but eventually condensing as the planet cools. This water carries with it organic compounds formed in the cold chemistry of interstellar space amino acids, nucleotide bases, simple sugars. The ingredients for complexity arrive ready-made from the cosmos, waiting only for stable conditions to begin their slow assembly into larger patterns. The mystery lies in timing. Mathematical models suggest that self-organizing chemical systems should emerge quickly once liquid water stabilizes, perhaps within a few million years. But the bombardment continues for hundreds of millions of years, repeatedly sterilizing the surface just as interesting chemistry begins. It's like watching evolution start over and over again, each promising beginning erased by the next cosmic collision. Only took 500 million years to delete everything that happened. Some impacts, paradoxically, might have aided rather than hindered the emergence of complexity. The energy released by large collisions creates vast hydrothermal systems, underground networks of heated water that remain active for millions of years after the initial catastrophe. These environments provide both the energy and the chemical gradients that modern theories require for the origin of life. Deep beneath the surface, protected from subsequent impacts, early forms of organization might have survived and evolved in darkness. The rock record preserves almost nothing from this time. The few surviving fragments date to the very end of the Hadean, when bombardment finally diminishes enough for stable crust to form. Everything earlier has been recycled through the mantle, melted and reformed beyond recognition. Geologists studying this period work more like archaeologists than traditional scientists, piecing together clues from isotopic ratios and mineral compositions, searching for signals hidden in the chemistry of rocks that formed billions of years later. One particularly intriguing mystery involves the carbon isotope ratios found in some Hadean zircons. Living processes preferentially incorporate the lighter isotope of carbon, leaving behind a distinctive signature that persists even when the original organic matter has long since vanished. Some of these ancient crystals show exactly this pattern, suggesting that biological activity, or at least complex organic chemistry, was already underway 4 billion years ago. But the evidence remains frustratingly indirect, like hearing an echo without being able to identify its source. The Hadean ends not with a dramatic event, but with a gradual settling, a slow decrease in the frequency and intensity of cosmic impacts. The asteroid belt finally stabilizes into predictable orbits. The inner solar system clears of the debris left over from planetary formation. Earth begins its long transformation from a molten wasteland into something resembling the world we know today. But by then, the slate has been wiped clean so many times that any earlier experiments in complexity have vanished completely. This is perhaps the most unsettling aspect of the Hadean amnesia. We know that the same physical and chemical laws operated then as now. We know that the ingredients for complexity were present. We know that stable conditions existed for millions of years at a time between the great impacts. Yet, we can never know what actually happened during those quiet intervals. What forms of organization might have emerged and flourished before the next cosmic catastrophe reset everything to molten chaos. The Hadean whispers its own dark possibility that complexity is not rare but ephemeral, emerging readily whenever conditions allow, but vanishing just as easily when those conditions change. Perhaps we are not the first to wonder about our predecessors. Perhaps the question itself, what came before, has echoed through multiple iterations of Earth's long experiment with organized matter. Only the planet itself remembers, and its memory has been burned away by the very forces that shaped it into a world capable of supporting complex life. The molten amnesia continues its work even now, more slowly, but just as certainly. Plate tectonics carries the ocean floors down into the mantle, where they melt and reform in endless cycles. Mountains rise and erode away. Continents drift and collide, grinding their histories into unrecognizable fragments. The evidence of our own presence will someday join the Hadean silence. Another set of whispers lost in the deep recycling of stone and time. The great unconformity cuts through the geological record like a surgeon's blade, removing vast chapters from Earth's story with surgical precision. Across entire continents, 1 billion years of rock simply vanishes, leaving behind only the contact zone where ancient foundations meet younger layers. Geologists trace this missing time from the Grand Canyon to the Scottish Highlands, from the Canadian Shield to the mountains of China, everywhere finding the same haunting absence where deep time should be. John Wesley Powell first described the phenomenon in 1869, floating down the Colorado River through layers of stone that told impossible stories. Above the unconformity, Cambrian limestones filled with the fossils of complex life trilobites with compound eyes, brachiopods with intricate shells, the sudden explosion of forms that marks life's entry into the fossil record. Below, Precambrian basement rocks stretch back toward Earth's beginning, their surfaces polished smooth by erosion and scored by ancient glaciers. Between these layers, a gap that spans more geological time than separates us from the earliest dinosaurs. The missing interval represents roughly 20% of Earth's entire history. During this vanished time, the planet experienced its most dramatic transformation since the origin of life itself. Oxygen levels rose and fell in great cycles. Supercontinents assembled and broke apart. Life evolved from simple bacterial films into the first complex cells, then into the earliest multicellular organisms. Yet, most of this story exists only in inference and theory. The physical evidence eroded away or buried beyond recovery. Scientists call these missing intervals unconformities, but the term understates their significance. These are not merely gaps in deposition, but active erasure. Periods when erosion outpaced the accumulation of new sediments. The Great Unconformity suggests that for hundreds of millions of years, entire continents stood above sea level, exposed to wind and weather, gradually wearing down to their crystalline cores. Rivers carved valleys deeper than the Grand Canyon. Glaciers scraped bedrock clean. Chemical weathering dissolved soluble minerals and carried them away in solution. The process operates with ruthless efficiency. Modern erosion rates, averaged across all the world's landscapes, remove roughly 2 inches of elevation every million years. Applied consistently over the missing billion years of the Great Unconformity, this would strip away approximately 2 miles of rock from every exposed surface. Mountains higher than the Himalayas could disappear completely, their existence known only from the scattered fragments they leave behind in distant sedimentary basins. This erasure creates a peculiar form of uncertainty. We know that life was evolving during the missing interval because we can trace the evolutionary relationships between simpler organisms below the unconformity and more complex ones above. But the intermediate forms, the transitional fossils that would show how this evolution proceeded, have been ground to sand and scattered across the planet. Only took 1 billion years to delete the evidence entirely. Some regions preserve fragments of the missing time in isolated basins where sediments accumulated faster than erosion could remove them. These windows into the lost interval reveal tantalizing glimpses of what vanished elsewhere. Stromatolites, layered mounds built by ancient microbial communities, suggest that organized life was already constructing large-scale structures. Trace fossils show evidence of burrowing organisms, the first animals to modify their environment through behavior. Chemical signatures hint at dramatic changes in ocean chemistry and atmospheric composition. But even these preserved fragments raise more questions than they answer. The stromatolites appear suddenly in the rock record, fully formed and highly organized, with no clear precursors. The trace fossils suggest complex behaviors without showing the organisms that made them. The chemical changes occur in patterns that seem to require biological explanation, but the biological agents remain invisible. It's like reading a book with most of the pages torn out, trying to reconstruct the plot from scattered paragraphs. The geographic extent of the Great Unconformity suggests a global cause, some planetary scale process that elevated continents worldwide and kept them above sea level for hundreds of millions of years. Some geologists propose massive glaciation, ice sheets thick enough to depress the underlying crust and expose vast areas to erosion when they finally melted. Others suggest a fundamental change in plate tectonics, a shift in the way continents moved and collided that altered the planet's topography. The exact mechanism remains debated, but the effect is undeniable, a systematic erasure of evidence across geological time. This vanishing creates space for speculation that science cannot easily address. If complex systems existed during the missing interval, their traces would be among the first casualties of continental erosion. Surface features disappear quickly on geological timescales. Even substantial modifications to the landscape cities, roads, mines would be reduced to scattered anomalies in mineral composition, easily attributed to natural processes we don't fully understand. The absence of evidence becomes perfect camouflage for the evidence of absence. Modern examples illustrate how quickly landscapes forget their history. The channeled scablands of eastern Washington preserve the scars of massive floods that occurred just 15,000 years ago. Yet these features are already softening under the influence of soil formation and vegetation growth. In 1,000,000 years, they will be nearly invisible. In 10 million years, completely erased. The timescales of the Great Unconformity dwarf these modern examples by factors of thousands. The unconformity also demonstrates the selectivity of preservation. Rocky coastlines erode rapidly, their materials transported to deep ocean basins where they accumulate as turbidites and abyssal sediments. But the ocean floors themselves are temporary features, recycled through subduction zones on timescales of a few 100 million years. Continental interiors preserve longer records, but only in areas that remain tectonically stable. Most of Earth's surface experiences burial and exhumation, heating and cooling, chemical alteration and mechanical disruption on timescales that exceed the survival of most evidence. The missing billion years whisper their own dark possibility that complexity leaves traces only under very specific conditions, and that most of the time, those conditions simply don't exist. Perhaps the fossil record we treasure, the preserved remnants of ancient life, represents not the normal state of affairs, but a rare convergence of factors that allowed evidence to survive. Perhaps the silence of deep time reflects not the absence of complexity, but the efficiency with which Earth erases its own experiments. The Great Unconformity continues its work today, more slowly but just as certainly. Mountains rise and weather away. Coastlines retreat under the assault of waves and storms. Glaciers advance and retreat, carving new valleys and polishing old surfaces smooth. Somewhere in the future geological record, our own time will become another unconformity, another gap where evidence should be but isn't, leaving future geologists to wonder what stories the missing rocks might have told. The Archean stromatolites rise from ancient seafloors like stone cathedrals, their layered domes and columns testament to Earth's first architects. These structures, built grain by grain over millions of years, represent something unprecedented in the planet's history. Life not merely surviving, but actively constructing, shaping its environment with deliberate precision. In the Pilbara region of Western Australia, 3.5-billion-year-old stromatolites stretch across entire hillsides, their bulbous forms creating landscapes that seem almost architectural in their regularity. Each stromatolite began as a thin film of cyanobacteria, photosynthetic microbes that trapped sediment particles in their sticky sheaths. As the film grew thicker, new layers formed on top, creating the distinctive laminated structure that characterizes these ancient monuments. The process required exquisite coordination among countless individual cells, each responding to light, chemistry, and the presence of neighbors in ways that produced coherent, large-scale patterns. Only took 1 billion years for life to discover construction. The builders themselves remain largely invisible in the fossil record. Cyanobacteria lack the hard parts that preserve well, leaving behind only indirect evidence of their presence, the chemical signatures of their metabolism, the textures they created in sediment, the precise arrangement of mineral grains that speaks to biological influence. Yet these traces tell a story of remarkable sophistication. The stromatolite builders were not random assemblages of cells, but organized communities, capable of collective behavior that transformed entire landscapes. Modern stromatolites in places like Shark Bay, Australia, offer glimpses into how these ancient ecosystems functioned. The microbial mats that build them operate like living carpets, with different species occupying distinct layers based on their tolerance for light, oxygen, and chemical gradients. Cyanobacteria dominate the surface, harvesting sunlight and producing oxygen. Below them, Purple and green sulfur bacteria thrive in the reduced conditions, recycling nutrients and maintaining the chemical balance that allows the entire community to flourish. The Archean versions were likely even more complex, built by communities that had been refining their collaborative strategies for hundreds of millions of years. Some stromatolites show evidence of seasonal growth patterns, suggesting that their builders could respond to environmental cycles in coordinated ways. Others display branching architectures that seem designed to maximize surface area for light capture, indicating a level of structural optimization that rivals modern engineering. The mystery deepens when considering the global extent of these structures. Archean stromatolites appear on every continent, in formations that span hundreds of kilometers and persist for millions of years. This suggests not isolated experiments in biological construction, but a worldwide phenomenon. Communities of builders that maintain their architectural traditions across vast distances and geological time. The consistency of their forms implies some form of information transfer, perhaps genetic or chemical signals that allowed successful designs to spread and persist. Some of the most intriguing examples occur in the Transvaal supergroup of South Africa, where stromatolites reach heights of several meters and display complex internal architectures. These structures required millions of years to build, their construction spanning timescales that dwarf human civilization. Yet they show clear evidence of planning and coordination, with internal channels that allowed water circulation and growth patterns that suggest response to changing environmental conditions. The builders faced challenges that would test any engineer. Archean oceans were rich in dissolved iron and other metals that could poison photosynthetic organisms. Volcanic activity was more intense than today, regularly disrupting coastal environments with ashfalls and toxic gases. Yet, the stromatolite communities persisted through these disturbances, often incorporating volcanic materials into their structures in ways that suggest adaptation rather than mere survival. The decline of stromatolites coincides with the rise of more complex life forms, particularly grazing organisms that could consume the microbial mats before they had time to build substantial structures. But their disappearance also corresponds to changing ocean chemistry, the gradual oxidation of seawater that altered the chemical gradients the builders depended upon. By the end of the Archean, 2 billion years ago, the age of microbial architecture was largely over, leaving behind only scattered examples in extreme environments where grazers cannot survive. The engineering principles embedded in these ancient structures continue to influence modern ecosystems. Microbial mats still build miniature stromatolites in hypersaline lakes and hot springs, using the same layered construction techniques their ancestors perfected billions of years ago. These modern examples demonstrate the stability of the architectural strategies, patterns of organization that have persisted across more than half of Earth's history. Perhaps most remarkably, the Archean stromatolites represent the planet's first large-scale modification by living organisms. Before their emergence, Earth's surface reflected only physical and chemical processes, volcanism, erosion, sedimentation driven by purely inorganic forces. The stromatolite builders introduced something entirely new, the systematic rearrangement of matter according to biological patterns. They created structures that would not have existed without their intervention, transforming random seafloors into organized landscapes. This transformation required not just individual intelligence, but collective behavior, the coordination of countless organisms toward shared goals. The stromatolite builders had to solve problems of communication, resource allocation, and structural engineering that challenge modern scientists. They developed techniques for managing chemical gradients, optimizing light capture, and maintaining structural integrity over geological timescales. only took 3 billion years for their solutions to become invisible to casual observation. The silence of their legacy creates its own form of mystery. If microbial communities could engineer landscapes on continental scales during the Archean, what other forms of biological construction might have emerged and vanished during Earth's long history? The transition from microbial to multicellular organization occurred gradually over billions of years, with countless intermediate stages that remain poorly understood. Some of these stages might have involved forms of collective behavior and environmental modification that left no clear traces in the fossil record. The Archean architects whisper their own quiet questions across deep time. If simple bacteria could coordinate the construction of structures visible from space, what might more complex organisms accomplish given enough time and stable conditions? The answer lies buried in stone and silence, in the gaps between what we know and what we can imagine, in the vast library of possibilities that Earth has been exploring for 4 billion years. The Great Oxidation Event unfolds across the planet like a slow-motion catastrophe, transforming Earth's atmosphere from a methane-rich haze into the oxygen-dominated mixture that modern life requires. This chemical revolution, beginning around 2.5 billion years ago, represents the most dramatic environmental change in Earth's history, a planetary-scale shift that creates new possibilities for complexity while simultaneously destroying the world that came before. The architects of this transformation are cyanobacteria, those same microscopic engineers that built the Archean stromatolites. But now their photosynthetic activity reaches a critical threshold, pumping oxygen into the atmosphere faster than natural processes can remove it. For nearly 1 billion years, this waste product of biological metabolism had been absorbed by iron dissolved in the oceans, creating the distinctive red bands of iron formation that mark the geological record. But the iron sinks, becomes saturated, and oxygen begins to accumulate in the atmosphere itself. The change occurs with geological swiftness, a few million years that reset the planet's chemistry entirely. Atmospheric oxygen rises from virtually zero to perhaps 1% of modern levels, still a trace gas by current standards, but enough to begin a cascade of chemical reactions that will reshape every environment on Earth. The methane that previously dominated the atmosphere reacts with the new oxygen to form carbon dioxide and water vapor, triggering a greenhouse crisis in reverse as the planet's ability to trap heat suddenly diminishes. Snowball Earth episodes follow in the wake of this atmospheric transformation. Global glaciations so severe they may have frozen the ocean solid from pole to pole. The loss of methane greenhouse warming, combined with the high reflectivity of ice and snow, creates a runaway cooling effect that plunges the planet into a frozen state that persists for millions of years at a time. These ice ages represent more than climate change. They constitute a complete sterilization of Earth's surface, burying any complex surface structures under kilometers of ice and grinding bedrock smooth with glacial action. Yet, the mystery lies not in the cooling itself, but in what preceded it. The billion years before the Great Oxidation Event, sometimes called the Boring Billion by geologists, show evidence of remarkable biological innovation. Complex cells with nuclei and organelles appear for the first time. Multicellular organisms begin their first experiments with cooperative living. Some formations suggest large-scale biological structures, organized systems that span kilometers and persist for millions of years. Only took a few million years of oxygen accumulation to erase most traces of these experiments. The chemical evidence tells a story of sophisticated metabolisms existing before the oxygen catastrophe. Isotopic signatures in ancient rocks suggest biological processes that could concentrate rare elements, perhaps even refine metals on scales that approach the industrial. Some formations show patterns of mineral distribution that seem to require coordinated biological activity, not random microbial films, but organized systems capable of directing chemistry across vast areas. The anaerobic world that oxygen destroyed may have supported forms of complexity we can barely imagine. Without the corrosive effects of atmospheric oxygen, organic molecules would have been far more stable, persisting in the environment for geological periods. Complex carbon compounds could have accumulated in ways impossible in our oxidizing atmosphere, creating chemical systems of extraordinary sophistication. The absence of oxygen also meant the absence of fire, allowing structures to persist that would be impossible in our combustible world. Some researchers propose that the pre-oxygen Earth supported something resembling a global metabolic network, with different regions specialized for different chemical processes connected by atmospheric and oceanic circulation. The methane-rich atmosphere could have supported complex organic chemistry in the gas phase itself, creating aerial ecosystems that vanished completely when oxygen made such systems chemically impossible. The transition to an oxidizing atmosphere would have been as catastrophic for these systems as a nuclear war would be for modern civilization. The timing of the Great Oxidation event itself suggests coordination rather than accident. Cyanobacteria had existed for hundreds of millions of years before the atmospheric transition. Their oxygen production balanced by natural removal processes, something changed to tip this balance. Perhaps a shift in ocean circulation or continental weathering patterns that reduced the planet's ability to absorb biological oxygen. But the rapidity of the change suggests a threshold effect, a critical point beyond which the old chemical system could no longer maintain itself. The iron formations that mark this transition tell their own story of systematic change. These distinctive rocks, with their alternating bands of iron oxides and silica, require very specific chemical conditions to form iron-rich oceans under an oxygen-poor atmosphere. Their global distribution suggests ocean chemistry that was remarkably uniform across the planet, maintained by biological processes that regulated iron concentrations with extraordinary precision. The end of iron formation deposition marks not just a chemical change, but the collapse of a planetary regulatory system. Traces of this lost world persist in the most unlikely places. Some ancient rocks contain organic molecules that could only have formed under reducing conditions. Fossil remnants of the complex chemistry that flourished before oxygen made such compounds unstable. Others show isotopic patterns that suggest biological processing of elements in ways that no longer occur on Earth's surface. These chemical fossils represent perhaps our only direct evidence of the sophisticated systems that the oxygen catastrophe destroyed. The survivors of this transition faced a world transformed beyond recognition. The organisms that thrived in the methane-rich, oxygen-free atmosphere either adapted to the new chemistry or retreated to the few remaining refugia where the old conditions persisted: deep ocean sediments, volcanic hot springs, the anaerobic depths of microbial mats. The surface of the planet became a hostile environment for the very organisms that had dominated it for billions of years. Yet from this catastrophe emerged new possibilities. Oxygen-breathing organisms could extract far more energy from organic matter than their anaerobic predecessors, opening pathways to complexity that had been energetically impossible before. The ozone layer that formed from atmospheric oxygen provided protection from ultraviolet radiation, allowing life to colonize previously lethal environments. The chemical diversity that oxygen enabled through its reactions with other elements created new ecological niches and evolutionary opportunities. The Great Oxidation event establishes a disturbing precedent in Earth's history that biological innovation itself can become catastrophic, that the success of one form of organization can completely eliminate the conditions that allowed other forms to exist. The cyanobacteria that triggered this transformation were not malicious. They were simply following their evolved programming to capture sunlight and split water molecules. But their collective success reshaped the planet in ways that ended the Archean world forever. This pattern of biological transformation suggests that Earth's history may be punctuated by similar events, moments when successful organisms fundamentally alter planetary chemistry and destroy the evidence of what came before. The oxygen catastrophe may have been the first such reset, but not necessarily the last. Perhaps complexity emerges repeatedly on Earth, only to be erased by its own success, leaving behind only chemical whispers and isotopic shadows in the rocks. Snowball Earth episodes grip the planet in ice so complete that the very concept of seasons becomes meaningless. 4 times during the late Proterozoic, beginning around 750 million years ago, glaciers advance from both poles until they meet at the equator, encasing the entire globe in a crystalline shell that reflects sunlight back to space with ruthless efficiency. These are not the gentle ice ages of recent geological history, with their rhythmic advance and retreat, but total planetary refrigeration events that lock Earth in frozen stasis for millions of years at a time. The Sturtian glaciation persists for perhaps 60 million years, longer than the entire Cenozoic era that encompasses the rise of mammals and the evolution of human consciousness. During this interval, average global temperatures plummet to minus 50 degrees Celsius, cold enough to freeze carbon dioxide from the atmosphere. The oceans become solid ice to depths of several kilometers, their surfaces polished smooth by howling winds that carry snow crystals like sandpaper across the planetary sphere. Only volcanic heat keeps small areas of liquid water alive in isolated pockets, refugia where life clings to existence in conditions more hostile than the surface of Mars. The ice leaves its signature in stone with geological precision. Tillites rocks formed from glacial debris appear in formations that could only have been deposited at sea level near the ancient equator. These massive boulders, some weighing hundreds of tons, rest in fine-grained marine sediments with no evidence of how they arrived except through the transport mechanisms of continental-scale ice sheets. The magnetic orientations of these rocks confirm their tropical origins, proof that glaciers once scoured landscapes where coral reefs would later flourish. Yet the mystery lies not in the ice itself, but in what the ice preserved. Glacial burial represents perhaps the most effective form of geological storage available on Earth's surface. Modern glaciologists studying Antarctic ice cores can read atmospheric chemistry from hundreds of thousands of years ago, trapped in air bubbles that have remained sealed since the ice formed. The Snowball Earth episodes created similar preservation conditions on a planetary scale, potentially storing evidence from Earth's pre-frozen history in ice sheets that persisted for geological ages. When the ice finally melts, it does so catastrophically. Volcanic carbon dioxide, accumulating in the atmosphere throughout the glacial period without being absorbed by weathering or photosynthesis, eventually creates a greenhouse effect so intense that global temperatures soar from minus 50 to plus 50 degrees Celsius in perhaps a few thousand years. The transition from total glaciation to extreme greenhouse conditions happens faster than most species can adapt, creating another reset mechanism that eliminates evidence of whatever complexity managed to survive in the Ice Age refugia. The cap carbonates that mark the end of each Snowball Earth episode tell their own story of dramatic environmental change. These thick limestone formations, deposited directly on top of glacial sediments with no transitional layers, suggest oceans so supersaturated with dissolved carbon dioxide that carbonate minerals precipitated spontaneously from seawater. The chemistry required for such massive carbonate deposition implies atmospheric carbon dioxide levels hundreds of times higher than today. creating acid rain so corrosive it could dissolve exposed rock surfaces in decades rather than millennia. During the ice ages themselves, life retreats to environments that seem impossibly extreme by modern standards. Hydrothermal vents on the ocean floor continue to support chemosynthetic communities, their energy derived from volcanic chemistry rather than sunlight. Hot springs create small patches of liquid water where photosynthetic organisms might survive, their warmth carving temporary refugia in the global ice sheet. Some models suggest that impacts from asteroids and comets could create temporary warm zones, brief windows of melted ice that might support complex life for thousands of years before refreezing. The preservation potential of these environments creates tantalizing possibilities. Complex organic molecules remain stable for millions of years under the reducing conditions that develop beneath thick ice sheets. Anaerobic organisms could build sophisticated structures in the ice-covered oceans, their constructions preserved in perfect detail when the water finally freezes solid. The pressure and chemical conditions under kilometers of ice might even allow forms of organization impossible under normal surface conditions. Evidence for such preservation appears in the strangest places. Some postglacial sediments contain organic compounds that seem far too complex to have formed in the harsh conditions immediately following ice sheet melting. Others show isotopic patterns that suggest biological processing during the glacial periods themselves, implying that life not only survived the frozen intervals, but remained metabolically active throughout them. The chemical signatures are subtle, easily attributed to poorly understood geological processes, but they whisper of hidden activity during Earth's most sterile-seeming episodes. The timing of the snowball Earth events coincides with other dramatic changes in Earth's history. The breakup of the supercontinent Rodinia occurs during the same interval, creating new ocean basins and altering global circulation patterns. The first appearance of complex multicellular life happened shortly after the final glacial episode, as if the ice ages somehow prepared the planet for biological innovation. Some researchers propose that the extreme environmental pressure of global glaciation actually accelerated evolution, forcing life to develop new survival strategies that proved useful when normal conditions returned. Modern analogies suggest how thoroughly ice ages could reset planetary surface conditions. The Antarctic ice sheet, covering an area smaller than a single continent, has preserved fossils and landscapes for millions of years in perfect detail. Expand this preservation to planetary scale, and entire ecosystems could be stored in glacial deep freeze, their evidence locked away until geological processes finally expose the ancient ice. The problem lies in recognizing such evidence when it appears, distinguishing between the products of glacial preservation and the normal processes of rock formation. The melting phases represent their own form of catastrophe. As ice sheets kilometers thick collapse, they release catastrophic floods that dwarf any modern disaster. Lake Missoula, which carved the channeled scablands of Washington state just 15,000 years ago, contained perhaps 2,000 cubic kilometers of water. The melting of a snowball Earth ice sheet would release millions of times this volume, creating floods that could scour continents clean and redistribute sediments on scales that approach continental drift. Any surface evidence of pre-glacial complexity would be swept away in the torrents, carried to deep ocean basins where it would be buried under kilometers of glacial outwash. The cycles themselves suggest regulation at planetary scales. 4 major snowball Earth episodes occur at roughly regular intervals, as if some feedback mechanism triggers glaciation whenever certain thresholds are exceeded. Some models propose that life itself creates the conditions for its own periodic destruction, perhaps through biological processes that gradually reduce atmospheric greenhouse gases until runaway cooling begins. Others suggest astronomical forcing, orbital cycles that periodically reduce solar energy input below critical levels. The chemical evolution of the oceans during these episodes remains largely unknown. Ice-covered seas would quickly become anoxic, their chemistry dominated by volcanic inputs and hydrothermal circulation rather than atmospheric exchange. Such conditions might support forms of aquatic life utterly different from anything in the modern ocean. Organisms adapted to low oxygen, high sulfur environments that vanish completely when normal ocean atmosphere interaction resumes. Only took a few million years for the ice to hide whatever was happening beneath. Each Snowball Earth episode erases evidence not just through burial and preservation, but through the catastrophic environmental changes that accompanied deglaciation. The transition from frozen to superheated conditions in a few thousand years represents environmental stress beyond anything in Earth's subsequent history. Whatever survives must be extraordinarily adaptable, capable of thriving in conditions that range from perpetual winter to tropical greenhouse. Most complex systems would fragment under such pressure, leaving behind only the most resilient components to seed whatever comes next. The Ice Ages whisper their own dark questions about planetary habitability. If Earth can freeze solid for millions of years and then thaw catastrophically, what other extreme states might be possible? The Snowball episodes demonstrate that stable climate is not guaranteed, that Earth's environmental systems can shift into alternative configurations that seem utterly alien by modern standards. Perhaps other forms of planetary scale change have occurred without leaving clear evidence, resets so complete they erase their own traces in the geological record. The Ediacaran fauna emerges from Earth's final ice age like phantoms materializing from the mist, their alien forms preserved in sandstone beds that span the globe from Australia to Newfoundland, from Namibia to the White Sea of Russia. These are the first large, complex organisms in Earth's fossil record, yet they defy every attempt at classification, their strange geometries belonging neither to the plant nor animal kingdoms as we understand them, for 30 million years, from roughly 570 to 540 million years ago. These enigmatic beings dominate Earth's shallow seas before vanishing as mysteriously as they appeared. Dickinsonia, perhaps the most famous of these ancient forms, grows as large as dinner plates, yet lacks any obvious means of feeding, moving, or reproducing. Its body consists of dozens of identical segments arranged in perfect bilateral symmetry, each segment slightly offset from the one behind, in a pattern that creates subtle spiral geometries. No mouth, no gut, no sensory organs, just a quilted disc that somehow maintained itself in the Precambrian seas. Recent chemical analysis of Dickinsonia fossils reveals cholesterol-like molecules that confirm its animal nature. Yet this only deepens the mystery of how such a creature could have survived without any visible means of nutrition. The entire Ediacaran ecosystem operates according to rules that seem to have been abandoned when complex life truly began. Charnia, resembling a modern sea pen, grows anchored to the seafloor in fractal patterns that maximize surface area for unknown purposes. Tribrachidium displays perfect three-fold symmetry, a geometric arrangement that never appears again in the fossil record, despite its mathematical elegance. Kimberella shows evidence of active movement across microbial mats, leaving behind feeding traces that suggest it could harvest nutrients from bacterial films, yet its body plan remains utterly foreign to any subsequent animal design. These organisms inhabit a world still dominated by bacterial mats, living carpets of microorganisms that cover vast areas of the seafloor in layered communities. The Ediacaran creatures seem adapted to this microbial landscape in ways that become impossible once burrowing animals appear and disrupt the bacterial foundations. Some researchers propose that the entire Ediacaran ecosystem represents an evolutionary experiment that reached a dead end when more familiar forms of life evolved the ability to engineer their environment through bioturbation and predation. The preservation of Ediacaran fossils themselves presents puzzles that challenge conventional understanding of how organic remains become stone. These soft-bodied organisms, lacking shells or skeletons, are preserved with extraordinary detail in sediments that show no evidence of rapid burial or other conditions typically required for fossilization. Instead, they appear to have been preserved through processes involving bacterial biofilms and unique chemical conditions that no longer occur in modern environments. The preservation is so perfect that even cellular details remain visible. Yet, the mechanism remains largely mysterious. Geographical distribution of Ediacaran sites suggests these organisms achieved global dominance with remarkable consistency. The same basic body plans appear on every continent, in formations that span millions of years, indicating not isolated evolutionary experiments, but a worldwide biosphere operating according to principles fundamentally different from those governing modern ecosystems. The uniformity of forms across vast distances implies either highly effective dispersal mechanisms or a level of environmental stability that allowed successful designs to persist unchanged for geological periods. Some of the most intriguing Ediacaran forms challenge basic assumptions about animal organization. Fractophusis displays a pattern of growth that resembles geological processes more than biological ones, its body expanding through fractal branching that creates self-similar structures at multiple scales. Ernietta constructs its body from identical modular units that can be assembled in various configurations, suggesting a fundamentally different approach to multicellular organization than the hierarchical tissue systems that characterize modern animals. The mystery deepens when considering the apparent lack of predation in Ediacaran ecosystems. None of these organisms show clear evidence of defensive structures, escape behaviors, or predatory adaptations. Bite marks, drill holes, and other signs of biological warfare that dominate later fossil assemblages are conspicuously absent from Ediacaran sites. This suggests either that predation had not yet evolved, or that these organisms possessed defensive strategies so effective they left no trace in the fossil record. Only took 30 million years for this peaceful world to end forever. Trace fossils from the late Ediacaran reveal the first evidence of complex behavior, with trackways and burrows that indicate organisms capable of directed movement and environmental manipulation. Yet, these traces often cannot be matched to any of the preserved body fossils, implying the existence of additional organisms that left behavioral evidence without preserving their physical forms. The gap between trace and body fossils suggests that the Ediacaran biosphere was far more diverse and complex than the preserved specimens indicate. The transition from Ediacaran to Cambrian represents one of the most dramatic discontinuities in the fossil record. The strange, quilted organisms of the Precambrian disappear almost entirely, replaced by the familiar arthropods, mollusks, and other phyla that dominate modern ecosystems. This replacement happens with geological suddenness, over perhaps 5 to 10 million years, suggesting either rapid evolution or rapid environmental change that favored entirely different forms of organization. Recent discoveries have extended the known diversity of Ediacaran life far beyond the classic forms preserved in shallow marine sandstones. Deep-water assemblages from South China reveal organisms with complex internal structures, some showing evidence of sophisticated circulatory systems or feeding mechanisms. These findings suggest that the visible Ediacaran fauna represents only a fraction of late Precambrian diversity, with most forms remaining unknown because they lived in environments less favorable to preservation. The ecological relationships among Ediacaran organisms remain largely enigmatic. Some appear to have been suspension feeders, filtering nutrients from the water column through mechanisms that leave no clear anatomical signatures. Others may have been osmotrophs, absorbing dissolved organic matter directly through their body surfaces without the need for digestive systems. Still, Others might have hosted symbiotic bacteria that provided nutrition through chemosynthesis or photosynthesis, creating partnerships that have no modern analogues. Chemical evidence from Ediacaran rocks suggests ocean conditions that would be toxic to most modern marine life. High levels of hydrogen sulfide, low concentrations of dissolved oxygen, and unusual trace metal abundances create a picture of marine chemistry that could support forms of life fundamentally different from those that evolved later. When ocean chemistry changed during the Cambrian transition, these alternative biochemistries might have become impossible, forcing the extinction of entire lineages that had thrived for millions of years. The mathematical precision of many Ediacaran forms hints at growth processes that operated according to simple geometric rules, rather than the complex developmental programs that control modern animal morphology. Fractophusis grows through repeated binary divisions that create perfectly self-similar structures. Tribrachidium maintains exact three-fold symmetry despite what must have been complex internal physiological processes. This mathematical regularity suggests that Ediacaran organisms might have discovered organizational principles that were later abandoned in favor of more flexible but less geometrically elegant solutions. The disappearance of the Ediacaran fauna creates one of paleontology's most enduring mysteries. These organisms dominated Earth's biosphere for millions of years, achieved global distribution, and showed clear evidence of complex organization and behavior. Yet, they vanish from the fossil record with almost no trace, leaving behind only chemical signatures and rare problematic forms that might represent evolutionary holdovers. Whether they were outcompeted, environmentally eliminated, or simply transformed beyond recognition remains unknown. Perhaps most unsettling is the possibility that the Ediacaran organisms represent just one of many experimental phases in Earth's biological history. Successful ecosystems that thrived for millions of years before being replaced by forms we consider more familiar. If complex organization can emerge, persist, and then vanish so completely that its basic operating principles become invisible, what other biological experiments might lie hidden in the gaps of the fossil record, their traces erased by the same processes that preserve the fragments we call evidence? The Cambrian explosion detonates across Earth's oceans like evolutionary fireworks, filling previously empty ecological niches with a bewildering array of body plans that seem to violate every principle of gradual change. In perhaps 20 million years, a geological instant complex animals with shells, eyes, limbs, and sophisticated nervous systems appear fully formed in the fossil record. Their anatomical innovations so complete they require no subsequent major revision. Trilobites scuttle across Cambrian sea floors with compound eyes containing hundreds of calcite lenses, each engineered to precise optical specifications that modern arthropods still employ 500 million years later. The speed of this transformation challenges conventional understanding of evolutionary processes. Darwin himself identified the Cambrian explosion as one of the most serious objections to his theory, noting that complex organs should require vast periods of gradual modification to achieve their sophisticated forms. Yet Cambrian eyes appear to have been perfected immediately, with no trace of the intermediate stages that should mark their development from simple light-sensitive spots to precision optical instruments. The same pattern repeats across multiple organ systems: gills, digestive tracts, circulatory networks, all appearing suddenly in their full complexity. Burgess Shale organisms reveal the true scope of Cambrian experimentation, preserving soft tissues in exquisite detail that illuminates the inner workings of these ancient ecosystems. Opabinia sports 5 eyes and a proboscis tipped with a grasping claw, an anatomy so bizarre it resisted classification for decades after its discovery. Hallucigenia walks on 7 pairs of spiny stilts while defending itself with dorsal spikes, its alien architecture defying every attempt to determine which end represents the head. Wiwaxia combines features of mollusks and annelids in configurations that suggest evolutionary relationships yet to be discovered. The preservation conditions that created the Burgess Shale assemblages occur only rarely in the geological record, typically requiring underwater landslides that bury entire communities in oxygen-free sediments before decay can destroy soft tissues. This rarity of exceptional preservation raises troubling questions about what remains invisible in the fossil record. If the Burgess Shale represents a brief window into Cambrian diversity, how many other experimental ecosystems existed during periods when preservation conditions were less favorable? Chemical evidence from Cambrian rocks suggests environmental changes that might have triggered the evolutionary explosion. Oxygen levels appear to have reached critical thresholds that made large, active organisms metabolically feasible for the first time. Ocean chemistry stabilized into patterns that allowed the precipitation of calcium carbonate shells, providing new possibilities for protection and structural support. But these environmental changes alone cannot explain the coordinated appearance of complex organ systems across multiple lineages simultaneously. The molecular clocks that estimate evolutionary timing tell a different story than the fossil record, suggesting that most major animal phyla diverged hundreds of millions of years before the Cambrian, during the mysterious intervals when the fossil record shows only simple organisms. This creates a paradox. Either the molecular estimates are wrong, or complex animals existed for vast periods without leaving recognizable traces. The possibility of a cryptic Precambrian biosphere, rich in soft-bodied organisms that rarely fossilized, haunts every interpretation of early animal evolution. Anomalocaris, the apex predator of Cambrian seas, reaches lengths of over 2 meters and possesses grasping appendages that could manipulate prey with precision approaching that of modern cephalopods. Its compound eyes, among the largest ever discovered, contain over 16,000 lenses arranged in geometries that maximize light-gathering efficiency and spatial resolution. Such sophisticated anatomy seems to require millions of years of refinement. Yet Anomalocaris appears in the earliest Cambrian deposits with no obvious predecessors. The ecological complexity of Cambrian communities rivals that of modern marine ecosystems, with clear evidence of predator-prey relationships, specialized feeding strategies, and niche partitioning among competing species. Trilobites show defensive spines that evolved in response to specific predators. Brachiopods develop elaborate filtering mechanisms that suggest competition for suspended organic matter. Some organisms construct the first complex burrow systems, creating three-dimensional habitat structures that persist in modified form throughout subsequent geological periods. Yet, beneath this apparent innovation lies a disturbing pattern of repetition. Many Cambrian body plans represent variations on themes that seem somehow familiar, as if the explosion was not creating entirely new forms, but rediscovering solutions to problems that had been solved before. The pentameral symmetry that characterizes echinoderms, the segmentation that defines arthropods, the bilateral organization that underlies vertebrate anatomy all appear suddenly as if following blueprints that predate their fossil manifestations. The geographic distribution of Cambrian fossils reveals coordinated changes across multiple continents, suggesting that whatever triggered the explosion operated on global scales. Similar assemblages appear simultaneously in formations from Siberia to South China, from North America to Morocco, indicating environmental or evolutionary pressures that transcended local conditions. This synchrony implies either rapid dispersal of evolutionary innovations or the activation of developmental programs that had been dormant across the biosphere. Trace fossils from the latest Precambrian show increasing complexity of behavior, with burrow systems that suggest organisms capable of three-dimensional thinking and long-term planning. The transition from simple horizontal trails to complex vertical shafts with multiple chambers happens over perhaps 5 million years, yet the behavioral sophistication implied by these structures seems to require neurological complexity that should have left other traces in the fossil record. Only took a few million years for intelligence to become invisible. The role of predation in driving Cambrian innovation appears central to the explosion's dynamics. The first clear evidence of predatory behavior coincides precisely with the appearance of defensive structures, shells, spines, protective behavioral patterns. This suggests an evolutionary arms race that accelerated morphological innovation beyond the rates seen in previous or subsequent periods. Yet, the sophistication of both offensive and defensive systems from their first appearance implies that the war was already well underway when it finally became visible in the fossil record. Some of the most intriguing Cambrian organisms combined features that later evolutionary theory considers incompatible. Opabinia possesses characteristics of both arthropods and mollusks, suggesting either primitive relationships among major phyla or convergent solutions to common environmental challenges. Waiwaxia displays structures reminiscent of both molluscan shells and annelid cartae, implying developmental pathways that were later abandoned or subdivided among separate lineages. The mathematical precision of Cambrian shell architectures rivals that of modern engineering solutions. Trilobite eyes employ optical principles that minimize spherical aberration and chromatic distortion. Brachiopod shells achieve maximum strength with minimum material through geometric arrangements that anticipate modern structural engineering techniques. Such optimization seems to require extensive trial and error refinement, yet appears fully developed in the earliest examples. The end of the Cambrian period sees a dramatic reduction in experimental forms, with many of the most bizarre body plans disappearing from the fossil record, never to return. This consolidation phase eliminates much of the anatomical creativity that characterized the explosion, leaving behind only those innovations that prove compatible with subsequent evolutionary pressures. The transition suggests that the Cambrian represented a period of unusual evolutionary freedom that later became constrained by ecological and developmental limitations, perhaps most mysteriously. The Cambrian explosion establishes developmental and anatomical frameworks that persist essentially unchanged for the next half-billion years. The basic toolkit of animal body plans, organ systems, and ecological strategies emerges during this brief interval and then remains remarkably stable through subsequent periods of environmental change. This stability suggests that the Cambrian innovations were not random experiments, but systematic solutions to fundamental problems of complex multicellular organization. The explosion whispers its own questions across deep time. If evolution can proceed so rapidly when conditions permit, what other episodes of dramatic innovation might be hidden in the intervals where preservation fails if complex organization can emerge so suddenly from apparently simple precursors? What forms of organization might have existed during the vast Precambrian periods when the fossil record shows only microbial mats and enigmatic traces? The Cambrian demonstrates that life's capacity for innovation far exceeds what the normal pace of evolutionary change would suggest possible. The Ordovician oceans stretch across a planet transformed, their chemistry written in limestone beds that span continents and persist for millions of years with remarkable consistency. These ancient seas, warmer and more alkaline than any modern ocean, support the most diverse marine ecosystems in Earth's history, while simultaneously recording chemical signatures that whisper of processes operating on scales that dwarf biological metabolism. Rare earth elements appear in concentrations that require explanation, their patterns suggesting systematic extraction and concentration by mechanisms that remain largely invisible in the fossil record. Brachiopods filter these alien waters through shells engineered with mathematical precision, their internal structures creating flow patterns that maximize nutrient extraction while minimizing energy expenditure. The most sophisticated examples employ complex internal baffles and chambers that direct water through carefully designed pathways, concentrating suspended organic matter with efficiency approaching that of modern industrial filters. Yet these organisms appear suddenly in the fossil record with their filtering mechanisms fully developed, showing no trace of the gradual refinement such engineering complexity should require. The reef systems that dominate Ordovician shallow seas operate according to principles that become extinct when the period ends. They're massive carbonate structures built by organisms that combine features of corals, sponges, and bryozoans in architectures that have no modern analogues. Stromatoporoid reefs extend for hundreds of kilometers along ancient coastlines, their internal frameworks creating three-dimensional habitat structures of extraordinary complexity. The builders coordinate their growth patterns across vast distances, maintaining consistent architectural themes that suggest some form of information transfer or genetic coordination that operates on continental scales. Crinoid meadows carpet the seafloor in formations so extensive they create their own local climate, their swaying stems generating currents that distribute nutrients and remove waste products with hydraulic efficiency. Individual crinoids achieve heights of several meters while maintaining structural integrity through calcite architectures that employ principles of tensioned engineering not rediscovered until modern skyscraper construction. The mathematical relationships governing their proportions mirror those found in optimal structural designs, suggesting evolutionary solutions that anticipate engineering principles by hundreds of millions of years. Yet the most intriguing aspects of Ordovician marine systems lie in their chemical signatures rather than their biological remains. Isotopic ratios of carbon, sulfur, and strontium show systematic variations that appear to require biological processing on scales that exceed any known metabolic activity. Some formations display rare earth element patterns that typically form only under conditions of extreme chemical concentration, as if vast volumes of seawater had been processed through biological systems capable of selective extraction and refinement. The trace metal abundances in Ordovician sediments tell stories of oceanic chemistry that seems impossibly organized. Platinum group elements appear in ratios that suggest large-scale separation processes, their concentrations following patterns that correlate with biological productivity indicators. Vanadium and molybdenum show systematic enrichments that typically require reducing conditions, yet occur in rocks that formed under the oxygen-rich conditions that characterized Ordovician seas. Only took 50 million years for these chemical anomalies to become invisible to casual observation. Graptolite colonies drift through the water column in formations that span entire ocean basins, their coordinated movements creating patterns visible in rock formations across multiple continents. These planktonic organisms construct elaborate branching colonies that seem designed for maximum efficiency in filter feeding. Yet their colonial organization displays mathematical relationships that suggest optimization beyond simple feeding requirements. Some graptolite assemblages show evidence of coordinated behavior across distances that exceed their communication abilities, implying organizational mechanisms that remain entirely mysterious. The volcanic activity that characterizes the Ordovician period occurs in patterns that correlate surprisingly well with biological productivity indicators, as if marine ecosystems somehow influenced or responded to tectonic processes operating deep within the Earth. Ash layers from massive eruptions show chemical compositions that reflect unusual source compositions. They're rare element signatures suggesting melting of crustal materials that had been previously enriched through unknown processes. The timing of major volcanic episodes coincides with biological innovations in ways that seem too regular to represent mere coincidence. Deep ocean sediments from this period preserve evidence of circulation patterns that distributed nutrients and trace elements with remarkable efficiency, creating chemical gradients that supported specialized communities across vast areas of the sea floor. The precision of these distribution patterns suggests regulatory mechanisms operating on oceanic scales, biological or chemical processes that maintained optimal conditions for marine productivity across millions of years. When these circulation patterns changed at the end of the Ordovician, much of the period's distinctive marine life vanished with them. The mass extinction that terminates the Ordovician represents one of the most severe biological crises in Earth's history, eliminating over 80% of marine species in two distinct pulses separated by perhaps 1 million years. The pattern of extinction suggests environmental changes that operated too rapidly for adaptation, yet the specific mechanisms remain debated. Glaciation certainly played a role, but the selective nature of the extinctions implies additional stresses that affected only certain types of organisms, while leaving others relatively unharmed. Chemical evidence from the extinction interval reveals oceanic conditions that would be lethal to most modern marine life. Hydrogen sulfide concentrations spiked to levels that would poison most oxygen-breathing organisms, while trace metal abundances suggest massive release of toxic elements from deep ocean sediments. Yet some organisms not only survive these conditions but appear to thrive, suggesting adaptation strategies or protective mechanisms that leave no clear traces in the fossil record. The recovery phase following the extinction shows patterns of biological innovation that seem remarkably coordinated, with new ecological strategies appearing simultaneously across multiple lineages. Burrowing organisms develop deeper and more complex infaunal communities. Filter feeders evolve more efficient mechanisms for extracting nutrients from increasingly oligotrophic waters. Predator-prey relationships reorganize into configurations that persist, essentially unchanged through subsequent geological periods. Perhaps, most remarkably, the chemical signatures that characterize Ordovician oceans never reappear in subsequent periods. Despite broadly similar environmental conditions during later intervals of warm climate and high sea level, the rare earth element patterns, trace metal concentrations, and isotopic ratios that define Ordovician marine chemistry represent a unique episode in Earth's history, suggesting processes that operated only during this interval before being permanently altered by the terminal extinction. The magnetic field evidence from Ordovician rocks indicates unusual patterns of geomagnetic behavior, with field reversals occurring at frequencies that exceed normal rates and intensity variations that suggest core dynamics different from those operating today. Some researchers propose that these magnetic anomalies reflect the influence of large-scale electrical currents in the oceans, perhaps generated by biological processes operating on continental scales. The correlation between magnetic field behavior and biological productivity remains unexplained but statistically significant. Modern attempts to recreate Ordovician marine chemistry in laboratory settings reveal that the unusual trace element concentrations require active biological mediation to maintain stability. Without constant biological processing, these chemical systems collapse within days or weeks, suggesting that the distinctive Ordovician ocean chemistry resulted from biological activities rather than purely geological processes. Yet the scale of biological processing required exceeds known metabolic capacities by orders of magnitude. The limestone formations that preserve Ordovician marine life show internal structures that suggest growth rates far exceeding those of modern carbonate systems, with some beds accumulating at rates that approach those of volcanic ash deposits rather than normal biological sedimentation. The mechanisms that could produce such rapid carbonate accumulation while maintaining the biological diversity recorded in these formations remain largely theoretical, requiring either environmental conditions that no longer exist or biological processes that have been lost to extinction. The Ordovician oceans whisper their own questions about the relationship between biological and geological processes on planetary scales. If marine ecosystems can influence oceanic chemistry to the extent suggested by the chemical evidence, what other forms of biological organization might be capable of planetary-scale environmental engineering? The patterns recorded in Ordovician rocks suggest that life's capacity for large-scale organization may extend far beyond what modern ecosystems demonstrate, leaving only chemical fossils to hint at the true scope of biological possibility. The Devonian forests rise from barren landscapes like Earth's first architectural experiment, their towering forms creating the planet's inaugural three-dimensional terrestrial ecosystems. Archaeopteris reaches heights of 30 meters while spreading lateral branches in geometric patterns that maximize light capture across vast areas. Its fern-like foliage creating the first forest canopies in Earth's history. These ancient trees engineer their own environment through root systems that extend horizontally for hundreds of meters, binding soil particles into stable substrates that persist for millions of years and creating the foundation for all subsequent terrestrial complexity. The transition from aquatic to terrestrial dominance happens with startling rapidity. The naked rock surfaces of the Silurian giving way to continuous forest cover across entire continents in perhaps 20 million years. This transformation requires innovations in structural engineering, water transport, and chemical defense that appear simultaneously across multiple plant lineages, suggesting either remarkable evolutionary coordination or the activation of developmental programs that had been prepared during earlier, poorly preserved periods of terrestrial experimentation. Lepidodendron grows to heights exceeding 40 meters while maintaining structural integrity through internal architectures that employ principles of biomechanical engineering not fully understood until modern materials science. These scale trees construct their trunks from modules that can be assembled in various configurations, creating structural flexibility that allows survival in unstable soils while maximizing vertical growth toward available light. The mathematical relationships governing their proportions mirror those found in optimal engineering solutions, yet appear fully developed in the earliest specimens without evidence of gradual refinement. The underground networks that support these forests operate with hydraulic sophistication that rivals modern urban infrastructure. Root systems extend laterally for distances that exceed tree heights by factors of 10 or more, creating interconnected webs that distribute nutrients and water across vast areas with remarkable efficiency. Some formations preserve root casts that suggest coordinated growth patterns among different species, implying communication or resource sharing mechanisms that leave no direct traces in the fossil record. Prototaxites, enigmatic organisms that may represent the largest terrestrial life forms of their time, tower 8 meters above the forest floor while maintaining trunk diameters approaching 2 meters. Recent analysis suggests these structures might represent giant fungi rather than plants, their internal anatomy consisting of interwoven tubes that could transport nutrients across continental distances. If fungal, they would represent biological networks operating on scales that exceed any modern terrestrial organism, suggesting forms of organization that became extinct when more familiar forest ecosystems developed. The chemical engineering that enables Devonian forest survival involves innovations in lignin biosynthesis that permanently alter the global carbon cycle. These structural polymers allow plants to construct rigid support tissues while resisting decay processes that would quickly recycle organic matter in aquatic environments. The accumulation of lignin-rich plant debris creates the first major terrestrial carbon reservoirs, beginning the process of coal formation that will eventually store millions of years of atmospheric carbon dioxide in underground deposits. Soil formation accelerates dramatically during the Devonian as plant roots and their associated fungal partners begin the systematic weathering of bedrock surfaces. Chemical secretions from root systems dissolve minerals with selectivity that approaches industrial acid processing, extracting specific elements while leaving others in concentrated forms that would be impossible through purely physical weathering. The resulting soil profiles show chemical gradients that suggest biological processing on scales that dwarf modern soil formation rates. The ecological relationships that develop within these early forests display complexity that seems to anticipate later evolutionary innovations. Some plant species show evidence of defensive compounds that specifically target herbivorous arthropods, suggesting co-evolutionary arms races that were already well established when they first became visible in the fossil record. Other species develop reproductive strategies that rely on arthropod pollinators, implying behavioral coordination between plants and animals that required sophisticated communication mechanisms. Arthropod communities within Devonian forests achieve sizes and diversity that have no modern parallels, with some millipedes reaching lengths of over 2 meters and dragonflies achieving wingspans approaching 1 meter. These gigantic forms suggest atmospheric oxygen concentrations significantly higher than modern levels, yet the physiological mechanisms that enabled such sizes remain poorly understood. The metabolic requirements of these large arthropods would have created nutrient cycling patterns that fundamentally altered forest ecosystem dynamics. The preservation potential of forest environments creates unique opportunities for documenting terrestrial complexity, yet also introduces systematic biases that might conceal as much as they reveal. Rapid burial in forest soils preserves delicate structures that would decay quickly in aquatic environments. But the three-dimensional nature of forest ecosystems means that most organic matter accumulates in locations where preservation is unlikely. Only took a few million years for these preservation biases to become invisible to paleontological analysis. Charcoal deposits from the Devonian provide evidence of frequent forest fires that seem to have been integral to ecosystem functioning rather than catastrophic disturbances. The chemical composition of these charcoals suggests combustion temperatures and atmospheric oxygen levels that would make modern forest fires seem gentle by comparison. Yet the rapid recovery indicated by plant succession patterns implies that these early forests had evolved sophisticated strategies for surviving and regenerating after fire episodes that would eliminate most modern ecosystems. The geographic distribution of Devonian forest assemblages reveals coordination across continental scales, with similar architectural solutions appearing simultaneously on different continents that were separated by vast ocean distances. This suggests either highly effective dispersal mechanisms or the independent discovery of optimal engineering solutions by different evolutionary lineages. The mathematical relationships governing tree architectures remain consistent across these geographic separations, implying fundamental physical constraints that channel biological innovation along predictable pathways. Root system architectures preserved in Devonian paleosols show evidence of underground spatial organization that seems designed to maximize resource extraction while minimizing competition among neighboring plants. Some formations reveal root networks that appear to be actively managed, with connections between species that suggest resource sharing or coordinated responses to environmental stress. The complexity of these underground relationships implies forms of plant communication that operate through chemical signals transmitted via fungal networks. The biochemical innovations that characterize Devonian plant evolution include the development of secondary metabolites that have no modern analogues, chemical compounds that served functions we can only guess at from their molecular structures. Some appear to be defensive compounds with specificity that suggests coevolution with particular herbivore lineages. Others might have functioned as communication molecules, enabling coordination among plants across the landscape-scale networks that root systems created. Sedimentary evidence from Devonian forest environments reveals patterns of nutrient cycling that seem impossibly efficient by modern standards, with phosphorus and nitrogen being retained within ecosystems at rates that approach 100%. This efficiency requires biological mechanisms that capture and recycle these limiting nutrients with precision that approaches industrial chemical processing. The specific mechanisms remain unknown, but their effects are clearly recorded in the chemical compositions of associated sedimentary rocks. The transition zones between aquatic and terrestrial environments during the Devonian show evidence of hybrid ecosystems that combined features of both domains in configurations that have no modern parallels. Some formations preserve plant assemblages that seem adapted for life in environments that fluctuated between terrestrial and aquatic conditions on seasonal or longer time scales. These transitional communities might have served as evolutionary laboratories where innovations in both terrestrial and aquatic adaptation could be tested and refined. The mass extinction that terminates the Devonian eliminates many of the most sophisticated forest architectures, leaving behind only simpler forms that give rise to later forest ecosystems. The specific environmental changes that drove this extinction remain debated, but the selective survival of certain architectural strategies suggests that forest complexity had exceeded sustainable levels under changing environmental conditions. The loss of these early forest innovations represents one of the least understood major extinctions in Earth's history. Perhaps most intriguingly, some Devonian forest formations preserve evidence of large-scale modifications to landscape topography that seem to require coordinated activity across entire watersheds. Valley systems show patterns of erosion and deposition that appear to have been influenced by vegetation in ways that channel water flow along specific pathways. These landscape engineering effects suggest that early forests were capable of environmental modification on scales that approach geological processes, leaving signatures that blur the boundaries between biological and physical Earth system dynamics. The Permian extinction unfolds across the planet like a slow-motion apocalypse, its effects so comprehensive that geologists mark it as the boundary between Earth's ancient and modern eras. Over perhaps 60,000 years, an instant in geological time, 96% of marine species vanish from the fossil record, along with 70% of terrestrial vertebrates and nearly all the complex forest ecosystems that had dominated landscapes for over 100 million years. When the killing finally stops, Earth emerges transformed into something resembling an alien planet, its surfaces scoured clean of most traces of the biological complexity that had accumulated since the Cambrian explosion. The Siberian traps begin their eruption around 252 million years ago, vomiting molten rock across an area larger than the continental United States, while simultaneously releasing volumes of carbon dioxide, sulfur compounds, and toxic metals that poison the atmosphere and oceans on a planetary scale. These are not ordinary volcanic eruptions, but flood basalt events that continue for hundreds of thousands of years. Their lava flows thick enough to bury entire mountain ranges, and their gas emissions sufficient to alter global climate beyond the tolerance limits of most existing life forms. Ocean chemistry collapses into conditions that would be instantly lethal to any modern marine organism, with hydrogen sulfide concentrations rising to levels that turn seawater into a toxic soup, while atmospheric oxygen plummets to perhaps 10% of current levels. The marine carbon cycle breaks down completely as carbonate-secreting organisms disappear, leaving behind only scattered populations of disaster taxa opportunistic species that can survive in environments too hostile for more specialized forms. Only took a few 100,000 years to reset 4 billion years of evolutionary innovation. Yet the pattern of extinction reveals selectivity that challenges simple environmental explanations. Some organisms vanish completely, while others, superficially similar in their ecological requirements, survive with minimal losses. Brachiopods, which had dominated marine filter-feeding niches for hundreds of millions of years, disappear almost entirely, while bivalves, employing broadly similar feeding strategies, survive to become the dominant filter feeders of post-Permian oceans. The differential survival suggests environmental pressures that operated at levels more fundamental than simple tolerance to temperature, acidity, or oxygen depletion. The terrestrial extinction proceeds with equal severity but different timing, with complex forest ecosystems collapsing before the marine crisis reaches its peak. Lycopsid forests that had dominated coal-forming environments since the Carboniferous vanish completely, their disappearance coinciding with the spread of more drought-tolerant plant communities that seem pre-adapted to the harsh conditions that follow. The coordination between terrestrial and marine collapses implies environmental changes that operated simultaneously across all of Earth's major ecosystems. Fungal spores dominate sedimentary layers from the extinction interval, their abundance suggesting that decomposer organisms briefly inherited the planet after the death of most primary producers. These fungal blooms represent perhaps the closest Earth has come to complete ecosystem collapse, with dead organic matter accumulating faster than living systems could process it. The chemical composition of these spore-rich layers reveals organic compounds that have no modern analogues, breakdown products of organisms whose biochemistry vanished with the extinction. The recovery phase that follows shows patterns of biological innovation that seem impossibly rapid, with new ecosystems assembling from the surviving fragments in configurations that anticipate subsequent evolutionary developments. Archosaurs, the group that will eventually give rise to dinosaurs and birds, appear suddenly in the fossil record with anatomical innovations that seem to require millions of years of prior evolution. Similarly, the first modern reef corals emerge with skeletal architectures that show no clear relationship to their Permian predecessors. Isotopic evidence from extinction boundary rocks reveals carbon cycle perturbations that exceed anything in Earth's subsequent history, with carbon isotope ratios shifting by amounts that require biological explanation, yet occur too rapidly for normal biological processes to accommodate. Some researchers propose massive releases of methane from oceanic hydrate deposits, triggered by initial warming that created runaway feedback loops, leading to even more severe climate change. Others suggest systematic destruction of organic carbon reservoirs through mechanisms that remain largely theoretical. The geographic distribution of surviving organisms shows patterns that suggest refugia existed in environments that have no clear modern analogues. Some species that vanish from most continents persist in isolated locations, where geological evidence indicates unusual chemical conditions, high sulfur concentrations, elevated metal contents, or other factors that should have been toxic to most life forms. These chemical refugia imply that some organisms had evolved tolerance to environmental conditions that became widespread during the extinction, but were previously restricted to specialized habitats. Trace fossil evidence from immediately post-extinction sediments reveals behavioral patterns that seem designed for survival in unstable environments. Burrow systems become deeper and more complex, with multiple escape routes and chambers that could provide protection from rapidly changing surface conditions. Some trace fossils suggest organisms capable of remaining dormant for extended periods, perhaps waiting for environmental conditions to stabilize before resuming normal activity patterns. The magnetic field evidence from Permian extinction rocks indicates geomagnetic behavior that differs significantly from normal patterns, with field reversals occurring at unusually high frequencies and intensity variations that suggest core dynamics influenced by external factors. Some researchers propose that the massive volcanic activity of the Siberian Traps created electromagnetic effects that disrupted normal geomagnetic processes, potentially affecting organisms that relied on magnetic navigation or whose biochemistry was sensitive to electromagnetic fields. Rare earth element patterns in extinction, boundary sediments show systematic enrichments that typically require industrial-scale processing to achieve. Their concentrations following patterns that correlate with biological productivity indicators from before the crisis. The specific mechanisms that could produce such enrichments remain largely theoretical, but their presence suggests that pre-extinction ecosystems were processing these elements in ways that ceased when the crisis eliminated the organisms responsible. The volcanic ash layers that characterize the extinction interval contain mineral compositions that reflect unusual source magmas, their rare element signatures suggesting melting of crustal materials that have been previously modified through unknown processes. The timing of these unusual eruptions coincides precisely with biological collapse, implying either cause and effect relationships that remain poorly understood or coincidences so remarkable they challenge probabilistic explanation. Recovery ecosystems show evidence of accelerated evolution rates that seem to violate normal constraints on morphological change, with new body plans appearing over timescales of hundreds of thousands rather than millions of years. Some paleontologists propose that the environmental stress of the extinction somehow activated dormant genetic programs, allowing rapid expression of evolutionary innovations that had been suppressed under normal conditions. Others suggest that ecosystem simplification removed competitive constraints that normally slow evolutionary change. The chemical signatures that characterize pre-extinction ecosystems never reappear in subsequent periods. Despite environmental conditions that seem broadly similar during later intervals of high temperature and elevated carbon dioxide, the specific biochemical pathways, ecological relationships, and biogeochemical cycles that had operated for hundreds of millions of years were permanently eliminated, suggesting that the extinction represented not just species loss, but the destruction of fundamental biological processes that could not be reinvented. Perhaps most unsettling is the possibility that the Permian extinction eliminated forms of biological organization that had required hundreds of millions of years to develop and that represented solutions to environmental challenges we can barely imagine. The mathematical precision of some pre-extinction biological structures, the chemical sophistication of certain metabolic pathways, and the landscape-scale coordination of some ecological processes suggest levels of biological organization that may have approached what we might consider technological capabilities, all erased so completely that their existence can only be inferred from chemical fossils and isotopic anomalies. The Great Dying whispers its own dark questions about the stability of complex systems and the permanence of biological achievements. If evolution can spend hundreds of millions of years developing sophisticated solutions to environmental challenges, only to have those solutions eliminated in a few 100,000 years of environmental crisis, what other forms of organization might have emerged and vanished during Earth's long history? The Permian extinction demonstrates that complexity, once lost, may be irreplaceable, its specific innovations vanishing forever into the silence of deep time. The Triassic recovery unfolds across devastated landscapes like life relearning how to live. Its patterns of innovation, following templates that seem oddly familiar despite emerging from the most severe biological crisis in Earth's history. New ecosystems assemble from scattered survivors with architectural precision that suggests not random experimentation, but systematic reconstruction along predetermined pathways. Archosaurs radiate into ecological niches that anticipate dinosaur body plans by millions of years, their anatomical innovations appearing with mathematical regularity that implies optimization towards specific functional targets. The marine realm rebuilds itself through successive waves of colonization that follow surprisingly predictable sequences, with filter feeders re-establishing complex reef systems, predators developing hunting strategies that mirror pre-extinction patterns, and bioturbators reconstructing seafloor communities with three-dimensional complexity that rivals Paleozoic standards. Yet, these reconstructed ecosystems employ organisms that share no obvious evolutionary relationships with their predecessors, suggesting either remarkable convergent evolution or the activation of developmental programs that transcend phylogenetic boundaries. Scleractinian corals appear in the fossil record with skeletal architectures that seem designed for maximum efficiency in carbonate precipitation, their polyp arrangements and internal structures displaying geometric relationships that optimize both structural strength and surface area for symbiotic algae. These innovations appear suddenly, fully formed, with no clear intermediate stages linking them to the simple coral forms that survived the Permian extinction. The mathematical precision of their colonial organization suggests engineering principles that require sophisticated coordination among thousands of individual polyps. The terrestrial plant communities that emerged during the Triassic recovery show patterns of ecological organization that seem to anticipate later evolutionary developments by tens of millions of years. Coniferous forests develop architectural strategies that maximize light capture while minimizing water loss, their needle arrangements and branch geometries displaying optimization that rivals modern engineering solutions. Some formations preserve evidence of forest-scale coordination, with individual trees adjusting their growth patterns in response to neighbors in ways that create landscape-level resource management systems. Therapsids, the mammal-like reptiles that survive the Permian extinction in greatly reduced numbers, undergo rapid diversification that produces ecological specialists with anatomical sophistication that seems to require millions of years of gradual refinement. Some develop dental batteries for processing plant matter with efficiency approaching that of modern ungulates. Others evolve predatory adaptations that anticipate mammalian carnivore anatomy in remarkable detail. The speed of these innovations challenges conventional understanding of evolutionary rates under post-extinction conditions. The ichthyosaur radiation represents perhaps the most dramatic example of evolutionary innovation during the Triassic recovery, with terrestrial reptiles returning to marine environments and developing fully aquatic body plans within perhaps 10 million years. These marine reptiles achieve anatomical convergence with modern dolphins that extends to minute details of bone structure, organ arrangement, and hydrodynamic optimization. The precision of this convergence suggests either remarkable coincidence or underlying developmental constraints that channel evolution along specific pathways regardless of phylogenetic starting points. Chemical evidence from Triassic recovery sediments reveals biogeochemical cycles that operate with unusual efficiency, processing carbon, nitrogen, and phosphorus at rates that seem to exceed the metabolic capabilities of the sparse post-extinction communities. Isotopic ratios suggest biological processing of elements in patterns that require coordinated activity across entire ecosystems. Yet the organisms responsible for this coordination remain largely invisible in the fossil record. Only took a few million years for these processing mechanisms to become routine aspects of ecosystem function. The magnetic field signatures preserved in Triassic rocks show patterns of geomagnetic behavior that correlate surprisingly well with biological recovery phases, suggesting relationships between core dynamics and surface biological processes that remain poorly understood. Some formations record magnetic field reversals that coincide precisely with evolutionary innovations, implying either causal relationships or timing coincidences that challenge probabilistic explanation. The mechanisms that could link deep Earth processes to biological evolution remain largely theoretical. Volcanic activity during the Triassic follows patterns that seem almost coordinated with biological recovery, with major eruptions occurring during periods of ecological transition and creating environmental conditions that appear to facilitate rather than hinder evolutionary innovation. The chemical compositions of these volcanic emissions include trace elements that are concentrated by biological processes, suggesting feedback relationships between geological and biological systems that operate on continental scales. The trace fossil record from Triassic recovery intervals reveals behavioral innovations that seem designed for life in unstable environments, with organisms developing burrowing strategies, feeding mechanisms, and reproductive patterns that provide resilience against environmental fluctuation. Some trace fossils suggest colonial behaviors that have no clear modern analogues, with evidence of coordinated activity among organisms that show no other signs of social organization. These behavioral innovations often precede anatomical changes by millions of years, implying that ecological strategies evolved before the morphological features that support them. Rare earth element distributions in Triassic sediments show systematic patterns that suggest biological concentration and processing on scales that approach industrial levels. Yet the organisms responsible for these processes leave no direct traces in the fossil record. The efficiency of this element processing requires mechanisms that exceed known biological capabilities, implying either unknown metabolic pathways or coordination among organisms that transcends individual physiology. The geographic distribution of Triassic recovery assemblages reveals simultaneous innovation across widely separated continents, suggesting either remarkably efficient dispersal mechanisms or independent discovery of similar solutions to common environmental challenges. The mathematical relationships governing organism proportions and ecological ratios remain consistent across these geographic separations, implying fundamental organizational principles that operate regardless of local environmental conditions. Some Triassic formations preserve evidence of symbiotic relationships that seem to anticipate later evolutionary partnerships, with organisms developing biochemical dependencies that require millions of years of coevolution to achieve stable integration. These relationships often involve metabolic pathways that complement each other with precision that suggests deliberate biochemical engineering rather than gradual evolutionary adjustment. The speed with which these partnerships develop challenges conventional understanding of coevolutionary processes. The developmental biology implied by some Triassic innovations suggests access to genetic programs that seem too sophisticated for the organisms expressing them, with simple ancestral forms producing descendants that display anatomical complexity approaching that of much later evolutionary stages. Some researchers propose that environmental stress triggers the expression of normally suppressed genetic pathways, allowing rapid access to evolutionary innovations that would normally require millions of years of gradual change. The ecosystem-level organization that emerges during Triassic recovery displays hierarchical structure that seems designed for maximum stability under variable environmental conditions, with redundant pathways for energy flow and nutrient cycling that provide resilience against disturbance. This organizational sophistication appears rapidly, within perhaps 5 million years of the Permian extinction, suggesting either remarkable evolutionary innovation or the reconstruction of organizational patterns that existed before the crisis. Climate modeling of Triassic conditions reveals atmospheric and oceanic circulation patterns that seem optimized for supporting the specific types of ecosystems that actually developed, as if environmental conditions were fine-tuned to facilitate particular forms of biological organization. The precision of this environmental biological matching implies either extraordinary coincidence or feedback mechanisms that allow biological systems to influence planetary-scale environmental processes. The Triassic recovery demonstrates that biological innovation can proceed at rates that seem impossible under normal evolutionary constraints. With new ecosystems assembling from catastrophic collapse in ways that suggest not random reassembly, but systematic reconstruction along templates that transcend the specific organisms involved. This pattern raises disturbing questions about the nature of biological organization and the possibility that complexity emerges according to rules that operate independently of the particular species that happen to express them. Perhaps most mysteriously, the Triassic recovery produces ecosystems that seem somehow familiar despite being constructed from entirely different evolutionary lineages, as if biological organization follows patterns that remain constant even when the organisms themselves change completely. This continuity across major evolutionary discontinuities suggests that Earth's experiments with complexity may be more systematic and repeatable than the apparent randomness of evolution would suggest, leaving open the possibility that similar patterns of organization have emerged multiple times during the planet's long history. The mathematical inevitability of complexity whispers through deep time like a cosmic equation solving itself across billions of years. Its variables, including planetary age, chemical diversity, energy gradients, and the fundamental tendency of matter to organize into increasingly sophisticated patterns. Statistical models of Earth's history suggest that given 4.5 billion years of stable conditions, the emergence of organized systems approaches mathematical certainty not once, but repeatedly, with each iteration building upon the chemical and physical foundations left by previous experiments in complexity. The Drake equation, originally formulated to estimate communicating civilizations in the galaxy, takes on haunting new significance when applied to deep time on a single planet. The probability of life emerging from non-living matter, once considered vanishingly small, appears robust when averaged across hundreds of millions of years and countless trillions of chemical reactions occurring in diverse environments across an entire world. The emergence of complexity from simple beginnings follows patterns that seem almost algorithmic in their predictability. Given sufficient time and stable boundary conditions, thermodynamic principles suggest that organized systems emerge spontaneously whenever energy gradients exist to drive the self-assembly of increasingly complex structures. Earth has maintained such gradients for billions of years through solar radiation, radioactive decay, and gravitational differentiation, creating countless opportunities for matter to explore the space of possible organizations. The second law of thermodynamics, often invoked to explain why complexity should decrease over time, actually predicts the emergence of organized systems as the most efficient way to dissipate energy gradients in complex environments. Chemical network theory demonstrates that once molecular systems achieve certain thresholds of diversity and connectivity, they spontaneously generate emergent properties that transcend the simple sum of their components. Earth's early oceans contained the necessary chemical diversity, while hydrothermal vents and other dynamic environments provided the connectivity required for network effects to emerge. The mathematical models predict that such systems should produce self-organizing cycles, hierarchical structures, and information processing capabilities with reliability that approaches inevitability. The fossil record, incomplete as it is, preserves evidence of at least 4 major evolutionary transitions that each represent quantum leaps in organizational complexity, the origin of life itself. The emergence of complex cells with nuclei and organelles, the development of multicellular organisms with specialized tissues, and the evolution of complex nervous systems capable of abstract information processing. Each transition occurs with timing that seems coordinated with planetary-scale environmental changes, suggesting that Earth's evolution provides regular opportunities for organizational innovation. Information theory provides another lens through which to examine the inevitability of complexity. The genetic code represents just one possible solution to the problem of storing and transmitting information in molecular systems, yet its mathematical properties error correction. Redundancy. Modularity seem optimized for evolutionary exploration of complexity space. If genetic systems emerged once on Earth, the probability that similar information storage mechanisms arose multiple times during billions of years of chemical experimentation approaches mathematical certainty. The rare Earth hypothesis argues that Earth's specific conditions, its size, orbital distance, magnetic field, large moon are so unusual that complex life should be extremely rare in the universe. But this argument assumes that complexity requires exactly the same conditions that produced our particular form of life. A more general mathematical approach suggests that any planet with liquid solvents, energy gradients, and chemical diversity should eventually produce organized systems, though their specific forms might be unrecognizable to us. Computational models of evolutionary processes demonstrate that once self-replicating systems exist, they inevitably explore increasingly complex forms of organization through mechanisms that are mathematically predictable. The dynamics of selection, mutation, and drift create evolutionary algorithms that systematically search the space of possible designs, with complexity emerging as a statistical inevitability rather than an improbable accident. Only took 1 billion years for these algorithms to discover multicellularity, nervous systems, and technological manipulation of the environment. The principle of convergent evolution suggests that similar environmental challenges produce similar organizational solutions regardless of evolutionary starting points. Eyes have evolved independently dozens of times. Flight has emerged repeatedly in different lineages. And social organization appears across taxa that share no recent common ancestors. This convergence implies that the space of viable organizational solutions is limited, with optimal designs being discovered repeatedly by different evolutionary experiments. Network science reveals that complex systems naturally evolve toward configurations that maximize both robustness and efficiency. Creating architectures that persist across environmental changes while maintaining high performance in information processing and resource utilization. Biological networks, neural networks, metabolic networks, ecological networks all show mathematical properties that emerge from self-organization rather than external design, suggesting that complexity follows discoverable laws rather than random chance. The archaeological implications of mathematical inevitability are profound and disturbing. If complexity emerges reliably, given sufficient time and appropriate conditions, then Earth's 4 billion-year history should contain multiple independent experiments in organization, some reaching levels of sophistication that might approach or exceed our own. The apparent absence of evidence for such complexity creates a paradox that challenges either our understanding of preservation processes or our assumptions about the inevitability of organization. Systems theory predicts that once complex systems achieve certain thresholds of integration and information processing, they begin to modify their environments in ways that enhance their own stability and growth. This environmental engineering creates positive feedback loops that accelerate the development of even greater complexity, leading to exponential rather than linear increases in organizational sophistication. Earth's history shows clear evidence of such acceleration during multiple intervals, yet most of these episodes remain poorly understood. The mathematics of self-organization suggests that complex systems naturally develop hierarchical structures, with higher-level patterns emerging from lower-level interactions in ways that create new forms of causal efficacy. These emergent properties allow systems to influence their own evolution in ways that transcend simple Darwinian selection, potentially leading to forms of organization that actively direct their own development towards specific goals or configurations. Game theory applied to evolutionary dynamics reveals that cooperation and coordination should emerge spontaneously in systems where individual success depends on collective performance. The mathematics predict that such systems will develop increasingly sophisticated mechanisms for information sharing, resource allocation, and collective decision-making, potentially leading to forms of organization that function as unified entities despite being composed of many independent components. Statistical mechanics demonstrates that large numbers of simple interacting components will spontaneously organize into complex patterns under a wide range of conditions, with phase transitions occurring when system parameters cross critical thresholds. Earth's history includes multiple intervals when environmental conditions approached such thresholds, creating opportunities for spontaneous organization that might have produced complex systems with no clear evolutionary precursors. The mathematical analysis of Earth's deep history suggests that our planet has experienced thousands of opportunities for complexity to emerge, persist, and potentially reach levels of sophistication that challenge our current understanding of what is possible through natural processes. The absence of clear evidence for most of these potential episodes of complexity might reflect limitations in our ability to recognize or preserve evidence of organization that operates according to principles we have not yet discovered. Perhaps most unsettling is the mathematical prediction that complex systems, once they emerge, should eventually develop the capacity to engineer their own environments so thoroughly that they become invisible to later observers. Their activities integrated so completely with natural processes that distinguishing between biological and geological phenomena becomes impossible. If such integration has occurred repeatedly during Earth's history, the planet itself might represent not a stage for the emergence of complexity, but the product of billions of years of environmental engineering by forms of organization that have learned to hide their activities within the normal functioning of planetary systems. The mathematics whisper across deep time that complexity is not the exception, but the rule, not the product of unlikely accidents, but the inevitable result of matter and energy operating according to discoverable laws across sufficient time and space. The question is not whether complexity has emerged repeatedly on Earth, but whether we possess the conceptual tools necessary to recognize its traces when they have been integrated so thoroughly with planetary processes that they appear to be nothing more than the normal operation of a world that has been shaped by intelligence for billions of years. The Anthropocene unfolds across Earth's surface like a geological signature written in concrete and steel, its traces destined to vanish into deep time with the same inevitability that erased the Permian forests and Ordovician reefs. In just a few thousand years, less than an instant in planetary terms, human civilization transforms the chemistry of atmosphere and oceans, moves more sediment than all the world's rivers combined, and creates synthetic compounds that never existed in Earth's previous history. Yet geological perspective reveals that even our most dramatic alterations will fade, leaving behind only the faintest chemical whispers to mark our passage through deep time. The urban infrastructure that seems so permanent from human perspectives represents essentially momentary arrangements of matter that cannot persist without constant maintenance and energy input. Concrete begins deteriorating within decades of construction. Steel corrodes to rust that weathers away in centuries. And even our most durable plastics decompose under ultraviolet radiation and microbial attack over timescales of thousands rather than millions of years. Within 10 million years, perhaps 20, the physical traces of human construction will have weathered to scattered anomalies in mineral composition that could easily be attributed to unknown geological processes. Nuclear isotopes provide perhaps the most persistent signature of human activity, with some radioactive elements persisting for millions of years while gradually decaying to undetectable levels. But even these traces will eventually fade, leaving behind only subtle shifts in isotopic ratios that require sophisticated analysis to distinguish from natural background variations. The nuclear age spans perhaps a century from first weapons testing to whatever endpoint awaits. A temporal interval so brief that its isotopic signature will appear as essentially instantaneous in future geological analyses. Mass extinction represents our most dramatic impact on Earth's biological systems. Yet the fossil record demonstrates that recovery from even the most severe extinction events proceeds with remarkable consistency over timescales of 5 to 10 million years. The species we eliminate will never return, but new forms of organization will emerge to fill vacant ecological niches with innovations that might surpass anything that existed before human influence. The mathematical patterns of post-extinction recovery suggest that biological diversity eventually exceeds pre-extinction levels, often within time frames that are geologically brief. The carbon dioxide we inject into the atmosphere will be absorbed by weathering processes that operate on timescales of hundreds of thousands of years, returning atmospheric chemistry to pre-industrial levels through mechanisms that have operated throughout Earth's history. Ocean acidification will be reversed as carbonate buffering systems equilibrate with the new atmospheric composition. Climate systems will stabilize around new equilibrium points that bear no trace of human influence, except perhaps in the timing of natural climate cycles that our emissions briefly perturbed. Agricultural modifications to Earth's surface, terraced hillsides, drained wetlands, cleared forests represent temporary arrangements that natural processes will erase within thousands of years once human maintenance ceases. Erosion will smooth artificial topography. Succession will restore forest cover, and hydrological systems will return to patterns determined by underlying geology rather than human engineering. Only took 10,000 years for human agriculture to reshape continental landscapes, only a few thousand more for natural processes to erase most traces of that reshaping. The chemical pollution that contaminates modern environments follows geochemical cycles that will eventually disperse synthetic compounds below detection thresholds or concentrate them in formations that future geologists might interpret as unusual mineral deposits. Heavy metals will be incorporated into sedimentary layers where they will remain until tectonic processes carry them into subduction zones and recycle them through the mantle. Organic pollutants will decompose through biological and chemical processes that have been operating for billions of years. Electronic technology, despite its apparent sophistication, consists primarily of common elements arranged in configurations that have no special resistance to natural recycling processes. Silicon returns to sand. Copper oxidizes and disperses, and rare earth elements scatter according to their chemical affinities rather than human intentions. The information storage that seems so important to human civilization represents physical arrangements of matter that have no particular stability in the absence of active maintenance systems. Transportation, networks, roads, railways, airports follow topographic patterns that reflect underlying geological structures, but their artificial surfaces will weather away to expose the original landforms that determined their routes. Bridges will collapse, tunnels will flood and fill with sediment, and the great engineering works that span continents will fragment into scattered ruins that erosion will gradually eliminate. The Roman roads that once connected an empire have already largely disappeared. Modern transportation infrastructure will follow similar trajectories over similar timescales. Domestic animals and agricultural crops represent biological modifications that will either return to wild-type forms through natural selection or go extinct if they cannot survive without human support. The breeds and varieties that human selection has produced are maintained only through constant intervention that selects against natural fitness in favor of traits useful to human purposes. Without this intervention, artificial biological forms will either evolve rapidly toward natural configurations or disappear entirely within a few generations. The most persistent traces of human activity may be the isotopic signatures left by fossil fuel combustion, subtle shifts in carbon isotope ratios that could remain detectable for millions of years in the right depositional environments. But distinguishing these signatures from natural carbon cycle variations requires detailed understanding of both human industrial processes and geological carbon cycling knowledge that would not be available to future investigators unless they independently developed similar understanding of planetary biogeochemistry. Even our space-based artifacts follow orbital mechanics that ensure most will eventually re-enter Earth's atmosphere and burn up, while those in stable orbits will be abraded by micrometeorites and solar radiation until they disintegrate into dust that joins the cosmic debris constantly raining onto Earth's surface. The few objects that escape Earth's gravitational influence will disperse through the solar system according to celestial mechanics that make their eventual recovery vanishingly unlikely. Archaeological evidence suggests that human civilizations can disappear with remarkable thoroughness even over historical timescales. The Indus Valley Civilization, which controlled territory larger than ancient Egypt and Mesopotamia combined, vanished so completely that its existence was unknown until the 20th century. If civilizations can become archaeologically invisible in just a few thousand years, technological signatures should fade even more rapidly when subjected to geological timescales. The mathematical models that predict human technological signatures in the geological record show exponential decay functions that reduce detectability below meaningful thresholds within timeframes that represent tiny fractions of Earth's total history. Our impact on planetary systems, dramatic as it seems from human perspectives, represents a brief perturbation that will be absorbed by natural variability within timescales that are geologically insignificant. Perhaps most sobering is the realization that our entire recorded history spans less than 1% of the time that has elapsed since the last major mass extinction, and represents an infinitesimal fraction of the time available for complexity to emerge, flourish, and vanish during Earth's billions of years of chemical and biological experimentation. The Anthropocene will join the countless other episodes of innovation and extinction that mark Earth's long exploration of possible forms of organization. Climate records preserved in ice cores and sediment layers show that Earth's environmental systems operate according to rhythms and timescales that dwarf human civilization, with natural variations that exceed anything human activities have yet produced. Our climate impacts will eventually be absorbed into these larger patterns, becoming indistinguishable from the background variability that has characterized Earth's atmosphere throughout geological history. The humbling perspective of deep time reveals that human civilization, for all its apparent permanence and global influence, represents just another ephemeral arrangement of matter and energy that will dissolve back into the planetary systems that gave it birth. Our cities will crumble, our technologies will rust away, our biological modifications will revert to natural forms, and our chemical signatures will fade until future investigators, if any exist, will find only scattered anomalies to mark our passage through the vast library of possibilities that Earth continues to explore. This is not cause for despair, but for wonder at the creative power of planetary systems that can generate such complexity from simple ingredients, allow it to flourish for brief intervals, and then recycle its components into new experiments whose forms we cannot imagine. The Anthropocene whispers its own questions about the countless other episodes of complexity that may have emerged and vanished during Earth's long history, leaving behind only chemical fossils and isotopic shadows to hint at forms of organization that once transformed planetary systems before dissolving back into the patient chemistry of stone and time. Questions crystallize in the silence between heartbeats of geological time. their answers scattered across billions of years, like fragments of a conversation too vast for any single perspective to comprehend. The absence of evidence whispers as loudly as its presence, creating spaces in the record where entire civilizations might have flourished and vanished, their traces dissolved by the same patient processes that continue to reshape Earth's surface with each passing millennium. In the gaps between what we know and what we can know, possibility takes root like life in the most unlikely places. The rock record speaks in chemical languages we are only beginning to learn, its isotopic ratios and trace element signatures encoding stories that unfold across timescales that challenge human comprehension. Each anomaly might represent natural processes we have not yet discovered, or it might mark the passage of organized systems that learn to work within planetary cycles so thoroughly that distinguishing their activities from background geology becomes impossible. The uranium enrichments in ancient ore bodies, the rare earth element patterns in sedimentary formations, the carbon isotope excursions that correlate with no known biological processes all whisper of agency operating at scales we struggle to imagine. Statistical inevitability suggests that Earth's 4 billion-year experiment with complexity should have produced organized systems multiple times, each iteration building upon the chemical and physical foundations left by its predecessors. The mathematical models are unambiguous given sufficient time, stable energy gradients, and appropriate boundary conditions. Matter explores increasingly sophisticated forms of organization with reliability that approaches certainty. Yet the evidence remains tantalizingly indirect, hidden in chemical signals that could represent either unknown geological processes or the integrated activities of systems that mastered planetary engineering so completely they became invisible. The Great Unconformity erases a billion years of surface history, but unconformities of various scales punctuate the geological record like systematic deletions in a vast archive. Each gap represents not just missing rock, but missing time, intervals when evidence was actively destroyed through erosion, metamorphism, or recycling into the mantle. During these lost periods, Earth continued its chemical and biological evolution, but the specific forms this evolution took remain forever unknowable. Perhaps some gaps conceal not empty intervals, but evidence too integrated with natural processes to be recognized as the product of organized activity. The Cambrian explosion demonstrates that complexity can emerge with startling rapidity when conditions permit. Yet the molecular clocks suggest that the genetic foundations for this explosion were laid hundreds of millions of years earlier during intervals when the fossil record shows only simple organisms. This cryptic Precambrian evolution implies that sophisticated biological systems can exist for vast periods without leaving recognizable traces, their activities hidden in chemical processes that appear to be purely geological. Snowball Earth episodes bury entire planetary surfaces under kilometers of ice, creating preservation conditions that could maintain evidence of complex surface activity for millions of years. When these ice sheets finally melt, they release catastrophic floods that redistribute materials on continental scales while simultaneously exposing preserved evidence from pre-glacial periods. Yet we find no clear traces of complex organization in the rocks that emerge from these episodes, only chemical anomalies that hint at biological processes operating under conditions we can barely imagine. The Permian extinction eliminates most evidence of the biological complexity that had accumulated over hundreds of millions of years. But the chemical signatures that remain suggest forms of organization that transcended individual species or even entire ecosystems. The rare earth element concentrations, the systematic isotopic patterns, the trace metal abundances that characterize pre-extinction rocks all point to biological processing on scales that approach industrial levels. If such processing was possible, using only the metabolic machinery available to Permian organisms, what might be possible given longer periods of evolutionary refinement. The Triassic recovery demonstrates that complex organization can reassemble from catastrophic collapse with remarkable speed and precision, following patterns that seem to anticipate later evolutionary developments. This suggests either extraordinary evolutionary innovation or the reactivation of organizational templates that existed before the crisis, but remained dormant until conditions favored their expression. If such templates exist, encoded in genetic systems or environmental processes, they might represent the legacy of previous experiments in complexity that achieved integration with planetary systems so complete their origins became invisible. Deep time operates according to rhythms that make human civilization appear as brief as a lightning flash. Yet our own rapid technological development demonstrates that organized systems can transform planetary chemistry within geological instants. If similar transformations occurred during Earth's deep past, their environmental impacts would appear in the rock record as sudden chemical changes that we typically attribute to volcanic activity, impact events, or other geological processes. The speed of technological change suggests that complex systems might develop the capacity for planetary engineering much more rapidly than geological processes can preserve clear evidence of their activities. The mathematical analysis of preservation probabilities reveals that most evidence of surface activity disappears within millions of years. But the same analysis suggests that certain types of evidence should persist for hundreds of millions of years under appropriate conditions. The absence of such long-term evidence either indicates that complex surface activity has never occurred on the required scales, or it suggests that successful complex systems learn to minimize their geological footprints as part of their survival strategies. Information theory provides frameworks for understanding how organized systems might encode their activities in ways that appear to be natural processes to observers who lack the appropriate decoding mechanisms. Modern ecosystems create chemical signals that require sophisticated analysis to distinguish from purely geological phenomena, suggesting that more advanced systems might achieve even more complete integration with planetary cycles. If such integration has occurred repeatedly during Earth's history, the planet itself might represent not a passive stage for the evolution of complexity, but an active participant shaped by billions of years of coevolution with organized systems. The emergence of consciousness in human lineages demonstrates that matter can organize itself into configurations capable of asking questions about its own origins and contemplating its own future. This self-reflective capacity appears to be an emergent property of complex neural networks. Yet the mathematical principles that govern such emergence should apply to any sufficiently complex information processing system. If consciousness represents a natural phase transition in the evolution of organized matter, it might have emerged multiple times during Earth's long history, each instance leaving behind only the chemical signatures of its problem-solving activities. Network theory reveals that complex systems naturally evolve toward configurations that maximize both robustness and efficiency, creating architectures that can persist through environmental changes while maintaining high performance in resource utilization and information processing. Such systems develop emergent properties that transcend the capabilities of their individual components, potentially leading to forms of organization that function as unified entities despite being composed of many independent parts. The mathematical models predict that such unified systems should eventually develop the capacity to modify their environments in ways that enhance their own stability and growth. Systems biology demonstrates that living networks can achieve remarkable feats of chemical engineering, concentrating rare elements, synthesizing complex molecules, and maintaining chemical gradients that would be impossible through purely physical processes. If such capabilities can be scaled up through evolutionary processes operating over millions of years, The resulting systems might achieve forms of environmental modification that blur the boundaries between biological and geological phenomena. The principle of convergent evolution suggests that similar environmental challenges should produce similar organizational solutions regardless of starting conditions or evolutionary pathways. If technological development represents a natural response to certain types of environmental challenges, it should emerge repeatedly in any system that achieves sufficient complexity and persistence. The mathematical inevitability of such emergence implies that Earth's long history should contain multiple independent experiments in technology, most of which remain invisible either because they achieved integration with natural processes or because their traces have been erased by geological recycling. Perhaps the most profound question whispered by deep time concerns not whether other forms of complexity have existed on Earth, but whether we would recognize them if we encountered their traces. Our understanding of what constitutes evidence of organization reflects our own particular history and technological development. Yet other pathways to complexity might produce signatures that appear to us as nothing more than unusual geological or biological phenomena. The chemical anomalies, isotopic patterns, and systematic behaviors that we attribute to natural processes might represent the integrated activities of systems that learn to work within planetary cycles so effectively that their artificial nature became undetectable. The silence of deep time contains its own form of presence, like the resonance that remains in a bell after its ringing has faded beyond the threshold of hearing. Each rock formation, each chemical signature, each gap in the record represents a moment when matter arranged itself according to laws we are still discovering, creating patterns that might encode information about forms of organization that existed long before conscious observers evolved to ask questions about their meaning. The answers lie scattered across billions of years of planetary history, waiting for minds sophisticated enough to recognize the questions they represent and humble enough to accept that some mysteries may remain forever beyond the reach of understanding, hidden in the vast spaces between what happened and what can be known. The questions settle into silence like sediment drifting through dark water, each grain carrying traces of time too vast for comprehension. Earth continues its patient rotation, carrying its cargo of stone and mystery through the cosmic night, while deep beneath the surface, the slow recycling of rock proceeds with the same rhythms that have operated since the planet's formation. In the spaces between heartbeats of geological time, possibility rests like seeds waiting for conditions that may never come, or that may have come and gone countless times before consciousness evolved to wonder about their flowering. The rocks maintain their vigil, holding their chemical secrets in crystalline vaults that will outlast any civilization, any species, any form of organization that emerges from Earth's patient experiments with complexity. They speak in languages older than life itself, their isotopic whispers carrying messages encoded before the first cells learned to harvest sunlight, before the first reefs built their calcium carbonate cathedrals, before the first forests cast shadows on naked stone. Each mineral grain remembers conditions that existed when the world was young, when anything seemed possible because nothing had yet been tried. Time flows like a river whose source and destination remain hidden beyond the horizons of knowledge, carrying with it the dissolved remnants of mountains that have risen and fallen, of oceans that have opened and closed, of life forms that have flourished and vanished without leaving clear records of their passage. The current moves with the steady persistence of natural law, neither hurrying towards some predetermined destination nor lingering to preserve the moments that seem most precious to temporary observers. Only the flow itself persists, and the eternal question of what it might have carried away in its endless journey toward the sea, in the deepest quietude of planetary time, where millions of years pass like seasons and entire evolutionary radiations flicker like brief summers, Earth dreams its slow dreams of possibility. The dreams are written in stone and chemistry, in the patient arrangement of atoms into configurations that explore the space of what matter can become when given sufficient time and appropriate conditions. Some arrangements persist for billions of years. Others last only moments before dissolving back into the matrix of possibility from which they emerged. All are part of the same vast experiment in organization that began when the first molecules learned to make copies of themselves and may continue long after consciousness has forgotten how to ask questions about its own origins. The silence deepens into something approaching peace. The profound stillness of a planet that has seen everything and remembers almost nothing, whose surface bears only the most recent chapters of a story that began before the oldest rocks were formed and will continue long after the youngest mountains have worn away to sand. In this silence, the question of what came before dissolves into the larger mystery of what it means for matter to organize itself into patterns complex enough to contemplate their own existence and humble enough to accept that some answers lie forever beyond reach, hidden in the vast library of time that Earth continues to write with each passing moment. Each grain of sediment, each chemical reaction that rearranges the elements into new possibilities for wonder. Sleep comes like geological time itself, slowly and completely, carrying consciousness down into depths where questions rest without answers and possibilities exist without need for proof, where the dreamer becomes one with the vast, patient dreaming of a planet that has been asking questions about itself for longer than stars have time to answer, and will continue asking long after the questioner has become part of the stone silence that holds all mysteries in its crystalline embrace, waiting for the next brief moment of awareness to emerge and wonder, once again, what stories the rocks might tell if only we knew how to listen to their whispers across the immensity of deep time.